Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. The story of galaxies, cosmic cities in the night. On a clear, moonless night, far from city lights, the sky becomes an infinite ocean of darkness studded with stars. Across that darkness arches a pale, luminous band, a gauzy river of light flowing from horizon to horizon. For millennia, humans have looked up at this silvery band with wonder. In myth and legend, it became a celestial road for the gods, a river of souls, or the spilled milk of a goddess strewn across the heavens. Before our cities lit the night and banished the stars, the Milky Way was a canvas for our imagination and a mirror of our yearning. People around the world named it in their own poetic terms: a straw way dropped by heavenly farmers, a silver river bridging lovers, a sky road for migrating birds, a spirit path for departed souls. Yet, even in their enchantment, those early stargazers could not imagine the true nature of that milky band. It would take centuries to discover that every wisp of that glow comes from countless distant suns, and that beyond the Milky Way lie other cosmic cities of stars, faintly visible as tiny smudges in the sky. What are these great star cities, these galaxies that form the grand architecture of the universe? How did we come to understand them, and what do they tell us about our own existence? Our journey begins with the story of how humanity slowly awakened to the true scale and wonder of the galaxies. From myth to discovery, the Milky Way and beyond. For most of human history, the Milky Way was a mystery. Even as ancient myths wove stories about its light, no one knew what it truly was. The breakthrough came in 1610 when Galileo Galilei turned his telescope to that milky band. What he saw astonished him. The smooth glow dissolved into countless faint stars. The Milky Way was not a cloud or the breath of gods. It was made of stars. This was our first glimpse of the galaxy's true nature. Still, the Milky Way was thought to be the entire universe, a lone island of stars in a vast, dark sea. As the centuries passed, a few bold thinkers began to suspect there might be more islands out there. In 1755, philosopher Immanuel Kant imagined that the faint cloud, like patches observed in the night sky, were actually other Milky Ways, island universes far beyond our own. In the 1800s, telescopes grew more powerful, and astronomers began to see structure in these mysterious patches. The Great Irish Telescope of Lord Rosse, for example, revealed a spiral form in the Whirlpool Nebula in 1845, a majestic pinwheel of light. Such sightings fueled speculation. Could these spiral nebulae be galaxies in their own right? Colossal systems of stars as vast as the Milky Way. The idea was daring and controversial. Many scientists insisted these nebulae must be nearby clouds of gas or clusters within our Milky Way, because imagining them as separate galaxies made the universe seem unthinkably large. Meanwhile, our understanding of the Milky Way itself was growing. In 1785, William Herschel attempted to map the Milky Way by counting stars in every direction, sketching our star system as a vast, flattened disk. Later, in the early 1900s, astronomer Harlow Shapley used pulsating stars in globular clusters to measure distances across the Milky Way. He discovered that those clusters formed a great halo centered not on Earth, but far off in the direction of the constellation Sagittarius. In other words, the center of the Milky Way was nowhere near our solar system. Our sun was tucked in the suburbs, tens of thousands of light years away from the galactic center. The Milky Way, Shapley found, was enormous, on the order of 100,000 light years across or more, and our place in it was humble. Yet the true nature of the spiral nebulae still hung in the balance. Were they part of this one huge galaxy, or separate galaxies altogether? On April 26, 1920, in Washington, D.C., A crowd gathered at the Smithsonian's Museum auditorium to hear a public debate about the scale of the universe. It was a historic showdown. Two astronomers, Harlow Shapley and Heber Curtis, argued over the scale of the universe. Shapley, armed with his measurements of the Milky Way's vast size, believed our galaxy was the only galaxy. Everything we saw, including the spiral nebulae, lay within it. Curtis, however, maintained that the nebulae were far outside our galaxy, perhaps as other galaxies unto themselves. They traded evidence before an audience, posing a profound question. Was the universe essentially one galaxy, or was our Milky Way just one of many? The answer arrived only a few years later, from the Mount Wilson Observatory in California. There, in 1923, astronomer Edwin Hubble peered through a 100-inch telescope, then the world's largest, and examined the Andromeda Nebula in exquisite detail. Amid the hazy glow of Andromeda, he identified a faint, Cepheid variable star, a type of star that waxes and wanes in brightness in a regular rhythm. Cepheids are valuable cosmic yardsticks. Their pulse period reveals their true brightness, which in turn can be used to calculate their distance. When Hubble calculated how far away this star was, the result was staggering, roughly 2.5 million light years. Far beyond the Milky Way's boundaries, Andromeda wasn't a nearby cloud at all. It was an entire galaxy of its own. Hubble's discovery was a watershed moment. It's said that upon seeing Hubble's evidence, Shapley conceded with awe, "Here is the letter that has destroyed my universe." The paradigm had shifted. The Milky Way was no longer the entire cosmos, but one galaxy among a multitude. In one stroke, the universe became immensely larger. The Milky Way was revealed to be just one galaxy among many. In the wake of Andromeda's measured distance, other spiral nebulae were likewise found to be far outside the Milky Way. Those tiny smudges and whirlpools on photographic plates resolved into myriad galaxies, each an island of stars. Our one-island universe had become an archipelago of galaxies, scattered through an expanding cosmos. By the mid-20th century, it was clear that the universe is teeming with galaxies. Astronomers began to catalogue the galaxies by the thousands, then millions. Estimates of the total number of galaxies climbed into the billions. Edwin Hubble himself, after proving the existence of other galaxies, went on to observe that galaxies are rushing away from one another, evidence that the universe is expanding from a primordial beginning. But it all started with that realization that the Milky Way is not alone. The word galaxy, once synonymous with our Milky Way, now described an entire class of colossal star systems. The night sky's faintest whispers of light became mighty galaxies in our understanding. In the span of a few decades, humanity's view of the cosmos was transformed. We went from a universe confined to one galaxy to a universe filled with countless galaxies stretching in all directions. The revelation was as humbling as it was exhilarating. Our Milky Way, with its billions of stars, was just one among billions more. The scale of creation had expanded beyond imagination. The stage was set to explore these newfound galactic realms, to ask what galaxies are made of, how they live and die, and what role they play in the grand story of the universe. Anatomy of a galaxy, stars, dust, and dark matter. What does a galaxy actually look like, up close? Picture a giant rotating pinwheel made of stars. In a typical spiral galaxy like our Milky Way, billions of stars are arranged in a flat, pancake-shaped disk that revolves around the center. Graceful spiral arms wind outward from a bright central region like glittering trails. Those arms are not solid arms at all, but patterns, density waves, where stars and gas bunch together. They mark where new stars are being born, lighting the arms with young, blue starlight and the pink glow of nebulae. Traces of dark, filamentary dust clouds weave through the arms, silhouetting the starlight. Closer to the center of the galaxy, the spiral arms give way to a bright central bulge, a crowded spherical hub of older reddish stars. At the very heart of that bulge, in the nucleus of the galaxy, lurks a powerful presence, a supermassive black hole. This monster, millions of times the mass of the Sun, anchors the core. Most of the time, it's invisibly quiet, swallowing the occasional drifting star or gas cloud. But it's there, a dark heart at the center of the galaxy's light. Surrounding it is a dense swarm of stars in the bulge, orbiting like bees around an unseen queen. Moving outward from the bulge, we transition into the disk of the galaxy, the broad, flat region where the spiral arms sweep around. Here is where the majority of a spiral galaxy's stars reside, including our own Sun. These stars orbit the galactic center in nearly circular paths as the entire disk rotates majestically. Our Sun, for instance, takes about 230 million years to complete one circuit around the Milky Way's center. Throughout the disk, we find vast clouds of gas and dust, the raw material for new stars. In fact, the spiral arms themselves are sites where this gas and dust have been compressed, triggering the birth of clusters of stars. It's within these stellar nurseries that bright young stars form and burn hot, illuminating their surroundings. Beyond the visible disk of stars, a galaxy extends further into a much fainter realm. Enveloping the galaxy is a vast halo of old stars, globular clusters, and something even more mysterious, dark matter. Scattered throughout this halo are ancient globular clusters, each a spherical swarm of very old stars orbiting the galaxy's center. The halo's stars are scarce and dim, so you'd barely notice them in a photograph. But the halo isn't empty. It's filled with an enormous amount of invisible mass. This is the galaxy's dark matter halo, a spherical cloud of matter we cannot see, but whose gravity we can feel. It's this dark matter that provides much of the gravitational glue holding the galaxy together, extending well beyond where the starlight fades out. In a real sense, the true size of a galaxy is defined not just by its starlight, but by this huge dark halo reaching far into space. All these components, the spinning disk with its spiral arms, the central bulge and black hole, and the extended halo of stars and dark matter, together form a single coherent system bound by gravity. A galaxy is like a cosmic ecosystem. Stars are born from gas, live out their lives, and die, often exploding and enriching the galaxy with heavier elements. Those elements mix into new gas clouds, seeding the next generation of stars. Over billions of years, this cycle of birth and death gives the galaxy its character. In our Milky Way, for example, generations of stars have come and gone, forging the elements that now make up our Sun, our planet, and even our bodies. Not every galaxy has the same structure, of course. Spirals like the Milky Way have distinct disks and arms. Other galaxies, called elliptical galaxies, are shaped more like rounded or football-shaped swarms of stars with no obvious disk or arms, essentially just big, puffy collections of stars. They tend to contain older stars and little gas and dust. And then there are irregular galaxies, which defy neat classification, with chaotic shapes often caused by gravitational encounters or mergers. But all galaxies share the same basic ingredients: stars, gas, dust, and dark matter, arranged in some unified form. Whether a galaxy is a flat spiral or a blob like elliptical, it will likely have a central concentration of stars and a surrounding halo dominated by dark matter. In a way, a galaxy is like a city of stars. It has a densely populated downtown, sprawling suburbs, and distant outlying regions that fade into the darkness. It is an enormous, self-contained society of stars orbiting together through space. Our Milky Way, for instance, contains hundreds of billions of stars, each as real and potentially as sun, like as our own, along with vast interstellar clouds and invisible dark matter. Yet despite this richness, on the scale of a galaxy, space is mostly empty. Stars are so far apart that if you shrank the Milky Way to the size of an earthly city, each star would be like a single grain of sand, separated from the next grain by blocks or miles of empty space. From the central black hole to the far-flung halo, a galaxy is a complex, gravitationally bound system. Every part affects the others. The black hole can influence the surrounding bulge. Supernova explosions from dying stars enrich the gas that forms new stars, and the dark matter's gravity guides the orbits of stars in the outskirts. This grand structure, stars, dust, gas, and dark matter dancing in unison, is what makes a galaxy more than just a random collection of matter. It's a self-organizing cosmic city, one that evolves and changes over time, but remains bound together by the inexorable pull of gravity. In the next part of our journey, we will look at how astronomers classify these galactic cities by their shapes and what those shapes reveal about the galaxy's histories. Galactic diversity, spirals, ellipticals, and irregulars. Galaxies come in a dazzling variety of shapes and sizes. In the early 20th century, Edwin Hubble devised a system to classify them, often depicted as a tuning fork diagram. At one prong of the fork are the elliptical galaxies, big, smooth balls of stars ranging from nearly round to elongated ovals. On the other prong are the spiral galaxies, flat disks with spiral arms, further divided into those with a central bar of stars and those without. In between, bridging the fork's handle to the prongs, are lenticular galaxies, disk, shaped like spirals but without visible arms, appearing as a smooth lens of stars. And off the neat ends of the fork are the oddballs, irregular galaxies that don't fit any simple shape. The spiral galaxies are perhaps the most visually striking. They look like cosmic pinwheels, with curving arms and sometimes a bar through the center. Our Milky Way is one such barred spiral, as is the nearby Andromeda galaxy. Spirals tend to have plenty of gas and dust, which fuels ongoing star formation in their arms. The presence of bright young blue stars and glowing nebulae gives the arms a speckled bluish tint, while the central bulge shines yellow, white with older stars. Spirals can have arms that are tightly wound or loosely trailing, and a given galaxy might have two prominent arms, or multiple fragmented ones. Despite these differences, when you see that classic spiral form, you're looking at a galaxy that is actively creating stars and has a dynamic, rotating disk. Elliptical galaxies, by contrast, are more like cosmic rugby balls or giant glowing halos. They lack the clear features of spirals: no arms, no disk, just a broad ellipsoid of stars. Some ellipticals are nearly spherical, others are stretched and elongated. These galaxies typically appear reddish or yellowish because they are dominated by older, cooler stars. Very little cold gas or dust remains in an elliptical, which means new stars are no longer forming there. Instead, an elliptical galaxy is a more quiescent system, a retired galaxy in terms of starbirth. Many ellipticals are also enormous. Some of the largest galaxies in the universe are giant ellipticals like M87 in the Virgo cluster, a monster galaxy with trillions of stars and a supermassive black hole at its core. These leviathans often sit in the cores of galaxy clusters, having grown by gobbling up smaller galaxies over time. Sitting between spirals and ellipticals are the lenticular galaxies. A lenticular galaxy has a central bulge and a disk like a spiral, but no spiral arms. It's as if the whirlpool pattern of a spiral galaxy has faded away, leaving just a smooth disk. Lenticulars often have used up or lost much of their gas, so they have little ongoing star formation, similar to ellipticals in that sense. Yet they still retain a flattened disk structure of stars. They might represent a transitional phase, perhaps a spiral galaxy that lost its gas, or maybe the product of mergers that didn't completely randomize the stars into a puffball. They tend to have older stars like ellipticals, and without arms they look more featureless, just a bright core and a faint disk fading outwards. Then there are irregular galaxies, which, as the name implies, refuse to be neatly categorized. Irregulars have ragged, blobby shapes with neither arms nor smooth symmetry. Many are small dwarf galaxies that simply don't have enough mass to form an organized structure. They might look like clumps of stars and gas without a clear center. Others have been distorted by gravitational encounters. A past close pass or collision with another galaxy may have torn them into chaotic shapes. The large and small Magellanic Clouds, companion galaxies to the Milky Way visible in the southern hemisphere's night sky, are classic examples of irregular galaxies. They are full of active star formation and nebulas, but lack the symmetry of a spiral. Irregulars remind us that not every galaxy is a majestic pinwheel or a serene ellipse. Some are cosmic train wrecks or nascent fragments still finding their form. These shapes aren't just cosmetic. They tell a story about a galaxy's history and life cycle. A spiral galaxy's supply of gas and abundance of young stars suggests it's in an active phase, still evolving gradually and relatively undisturbed. An elliptical galaxy, full of old stars and little gas, likely has experienced a more violent past. In fact, astronomers believe that many ellipticals are the result of galactic mergers. When two spiral galaxies collide and merge, the immense gravitational chaos can scramble their disk structures and trigger bursts of star formation that eventually use up the gas. The end product is often an elliptical galaxy, a big ball of stars that used to be two separate spirals. In the dense environments of galaxy clusters, where collisions are more frequent, we see many ellipticals, hinting at this violent upbringing. Lenticular galaxies might tell another evolutionary tale, perhaps a spiral that slowly lost its spiral arms. Imagine a spiral galaxy that falls into a cluster of galaxies. As it plows through the hot gas in the cluster, it can be stripped of its own gas. With its star forming fuel removed, its arms would fade and cease to be obvious. What remains would be a lenticular, a disk of mostly older stars, quietly flying on without the youthful sparkle of arms. Thus, a galaxy can morph from a star, forming spiral into a more passive lenticular if the conditions take away its gas. Over time, even that disk might puff up through minor collisions or dynamic interactions, potentially becoming more elliptical. Irregular galaxies often represent youth or disruption. Some could be young galaxies that haven't settled down. In the early universe, many galaxies were clumpy and irregular before they coalesced into spirals or ellipticals. Others are simply what happens when galaxies gravitationally torment each other. An otherwise normal spiral can be twisted out of shape by a close pass with another galaxy, becoming irregular in the aftermath. In that sense, irregulars sometimes are like the before and after snapshots of galactic evolution, the building blocks that will later form larger galaxies, or the mangled remnants after a collision. Galactic morphology is a bit like a family album of galaxies. Spirals with their youthful star forming glow, ellipticals with the faded glimmer of old age, and lenticulars and irregulars as the in-betweens and outliers. By classifying galaxies, astronomers glean insight into how galaxies live and change. We see that galaxies are not static. They can transform. Graceful spirals can merge and swell into giant ellipticals. Small dwarfs can be cannibalized by bigger galaxies. Collisions can shatter a galaxy's symmetry or spark new stars. The shape we observe is a snapshot of a galaxy's ongoing story. This diversity in form is a testament to the myriad paths galactic evolution can take. It reminds us that each galaxy we see in the telescope, whether a perfect spiral or an amorphous smudge, has a unique history written in its shape and stars. Understanding these classifications and what they imply sets the stage for exploring how galaxies are born, grow, and sometimes die, a story that begins in the aftermath of the Big Bang and continues to unfold across cosmic time. Origins and evolution, from the Big Bang to today. Galaxies have not always filled the universe. There was a time, shortly after the Big Bang, when no galaxies existed at all, no stars, no structures, just a hot, dense fog of energy and subatomic particles. But even in that primordial chaos, tiny ripples in density were present. As the universe expanded and cooled, these slight fluctuations, quantum wrinkles stretched to cosmic scales, became the seeds of all future structure. Gravity began to amplify them. Regions just a bit denser than average slowly pulled in more matter. In the earliest epochs, matter in the universe was mostly hydrogen and helium gas, along with a much larger share of invisible dark matter. Dark matter doesn't interact with light, so as the universe cooled, it was free to clump together quickly, unhindered by radiation pressure. It formed an invisible scaffolding, a cosmic web of filaments and knots, into which ordinary gas flowed. Within a few 100 million years after the Big Bang, some of these knots of dark matter and gas had grown dense enough to ignite the first stars. These stars, we call them population 3 stars, were unlike any that exist today. They were likely extremely massive, bright, and short-lived, made of pristine hydrogen and helium. They lived fast and died young, some exploding as supernovae that enriched their surroundings with the first heavier elements like carbon, oxygen, and iron. With the birth of the first stars, the first proto-galaxies emerged. They might not have looked like the grand galaxies we see now. More likely, they were small, clumpy collections of stars. Perhaps only thousands or millions of stars bound together. But they were the seeds of future galaxies. Over the next few 100 million years, these fledgling star clusters began to merge and gather. Gravity drew proto-galaxies toward each other, combining them into larger structures. By 1 billion years after the Big Bang, the universe was becoming a cosmic cityscape of early galaxies. Many of them were irregular and turbulent, actively forming stars at a ferocious rate. The ultraviolet light from these newborn galaxies helped end the cosmic dark ages by ionizing the hydrogen gas in intergalactic space, making the universe transparent to starlight. As time went on, small galaxies merged into larger ones in a hierarchical fashion, like streams converging into rivers. This process of hierarchical merging meant that big galaxies grew at the expense of smaller ones. Every merger was a dramatic event. When two galaxies collided, their stars typically passed by each other, but their clouds of gas slammed together, triggering bursts of new star formation. The merging galaxies' shapes distorted, sometimes coalescing into a new form. Through countless such mergers and acquisitions, galaxies kept growing. A large galaxy like our Milky Way likely assembled from the amalgamation of many smaller progenitors over billions of years, each merger adding to its mass and mixing up its stars. Meanwhile, galaxies also grew by a quieter method, accretion of gas from their surroundings. Along the filaments of the cosmic web, tendrils of gas continued to funnel into galaxies, especially in the early universe. This fresh gas was fuel. It settled into rotating disks and kept star formation alive. In fact, even as major mergers built up the bulk of galaxies, a steady flow of intergalactic gas helped form extended disks and spiral structures. In galaxies that didn't undergo disruptive collisions for a long stretch, well, ordered disks had time to develop, the kind we see in majestic spiral galaxies. The Milky Way, for instance, has likely enjoyed a relatively quiet life for the past several billion years, allowing it to maintain its spiral disk and keep forming new stars at a modest rate by accreting gas. Galaxies also evolve internally. As generations of stars live and die within them, the galaxy's content changes. Early stars forged new elements and spread them out when they died, gradually enriching the galaxy's gas with heavier elements. This means later generations of stars, like our Sun, were born from material that had been recycled through previous stars, including elements crucial for planets and life. Over billions of years, the rate of star formation in the universe rose to a peak, and then declined. That cosmic high noon, when galaxies were churning out stars at record pace, is long past. Many galaxies today are less active, having used up or lost much of their star, forming fuel. The environment around a galaxy plays a big role in how it evolves. A galaxy, floating relatively alone, might keep its gas and continue forming stars for a very long time. But a galaxy in a crowded cluster can have a much harsher life. As it plunges through the thin, hot plasma that fills galaxy clusters, its own gas can be stripped away like leaves torn off a moving car. With its gas gone, its star formation can slow to a halt, turning a once blue spiral into a gas, poor lenticular or elliptical over time. Also, frequent interactions in a cluster, small gravitational tugs from many neighbors, can stir up a galaxy's structure, making spiral arms disheveled or triggering periodic bursts of star formation until the gas is exhausted. Throughout cosmic time, mergers big and small continued to shape galaxies. Two sizable galaxies merging can transform their structures, often yielding an elliptical galaxy and perhaps fueling a quasar as their central black holes ignite. Minor mergers, where a big galaxy cannibalizes a smaller one, are common too. Our Milky Way is in the process of digesting several dwarf galaxies even now, their stars forming streams in our halo. Every such event adds stars to the larger galaxy and can jostle its structure slightly. Galactic evolution is thus a complex tapestry woven from smooth flows of gas, violent collisions, internal fireworks of star birth and death, and environmental influences from the cosmic neighborhood. Over 13.8 billion years, galaxies have grown from tiny embryonic fluctuations into the grand systems we see today. Many started as little more than glimmering irregular clumps. Some settled into stable rotating disks. Others underwent repeated smash-ups that left them as giant ellipticals. Some, especially smaller ones, remain irregular to this day, perhaps never having the chance to form a tidy structure. One intriguing aspect of galaxy evolution is the co-evolution of galaxies with their central black holes. Almost every large galaxy has a supermassive black hole in its core, and somehow these black holes grew in tandem with their galaxies. In the early universe, frequent mergers and copious gas likely fed the black holes, turning some into blazing quasars. There's a curious correlation today. The mass of a galaxy's central black hole closely relates to the mass of the galaxy's bulge of stars, hinting that galaxies and black holes regulated each other's growth. It's a bit of a chicken or egg problem. Did big galaxies form first and then their black holes? Or did black holes form and help shape galaxies? But evidence suggests an intricate feedback dance. For example, a quasar can unleash so much energy that it blows gas out of the host galaxy, quenching further star formation for a time. Thus, the evolution of a galaxy is tied not only to external events, but also to the sometimes fierce influence of its own central engine. From the primordial gas collapsing into the first star clusters, to the grand collisions that built up cluster giants, galaxy evolution spans the entire history of the universe. It's still ongoing. Even now, galaxies continue to interact and grow. Our local group of galaxies is quiet at the moment, but the Milky Way and Andromeda are drifting inexorably closer and will merge billions of years from now, reshaping into a new, larger galaxy. Eventually, as eons pass, galaxies will use up much of their gas and star formation will slow to a trickle. The night skies of the far future may be dominated by aging red stars and fading galaxies. But for now, in this epoch, galaxies of all types still populate the cosmos, from lively spirals to sleepy ellipticals, each a product of the rich evolutionary journey that took it from the aftermath of the Big Bang to the form we observe today. When galaxies collide, cosmic encounters and mergers. Galaxies are not static, isolated islands. They often interact, and sometimes collide in a slow motion dance governed by gravity. Imagine two enormous cities drifting toward each other over eons. As the galaxies draw near, their mutual gravity stretches and warps them. Long tidal tails of stars are drawn out, and great arcs of gas are flung into intergalactic space. If we could watch this unfold, we'd see the two galaxies distort like taffy being pulled, perhaps looping around each other once or twice. Over hundreds of millions of years, they may sway back and forth in a gravitational embrace before eventually merging into one. Despite the word collision, individual stars almost never hit head-on during these encounters. The distances between stars are just too vast. The galaxies pass through each other like ghosts, but gravitational forces wreak havoc on their structures. The delicate spiral arms of a spiral galaxy can be torn apart or twisted into new shapes. In some cases, a smaller galaxy plunging through a larger one can spark a graceful ring galaxy like a ripple in a pond. In other cases, two spiral galaxies entangle, throwing out twin tidal tails of stars. The colliding antennae galaxies are a beautiful real example, their long filaments of stars and gas arcing out like insect antennae as their disks intersect. Within the antennae, telescopes see countless young star clusters ignited by the collision. It's a glimpse of what our own Milky Way might undergo in its future encounters. One of the most dramatic effects of a galactic collision is on the galaxy's gas. When galaxies collide, their vast clouds of gas slam into each other. Unlike stars, gas clouds do collide, compressing violently. This compression can ignite a starburst, a sudden surge of star formation. In the aftermath of a collision, the merging galaxies may glow with the light of countless newborn stars, a fireworks show that can outshine a normal galaxy. The antennae galaxies, for instance, are experiencing such a burst of star birth as they merge, with brilliant clusters of young stars lighting up the wreckage. In addition, as the two galaxies coalesce, their central supermassive black holes will eventually spiral toward each other and merge as well, potentially releasing a burst of gravitational waves. Over time, the result of a major merger is often a single, more massive galaxy. Two spiral galaxies colliding will likely settle into an elliptical galaxy, their orderly disks destroyed, their gas largely converted into stars or expelled, leaving a big ball of stars. The chaos of the merger tends to randomize the orbits of stars, which is why the end product has that puffy, elliptical shape rather than a flat disk. We see evidence of past mergers in some galaxies today. Giant ellipticals often have faint shells or ripple patterns of stars around them, the ghostly remains of smaller galaxies they absorbed. Our own Milky Way shows signs of past minor mergers too. Streams of stars in the halo mark where dwarf galaxies were torn apart and assimilated. Even small interactions can leave lasting impressions. A flyby of a smaller galaxy might induce spiral arms or bars in a larger galaxy, or cause a burst of star formation by jostling its gas. Galaxies can also cannibalize their companions. A big galaxy like the Milky Way can slowly consume a small satellite galaxy, pulling it apart over billions of years. In fact, the Milky Way is doing this right now to at least two known dwarfs, their stars being strung out into lengthy loops around our galaxy as they are assimilated. These minor mergers are gentler than a head-on collision of equals, but they still contribute to a galaxy's growth and can subtly disturb its structure. One collision in particular stands out to us because it lies in our future: the anticipated encounter between the Milky Way and the Andromeda Galaxy. Andromeda, currently about 2.5 million light-years away, is on a slow collision course with us, due to meet our Milky Way in about 4 billion years. Though that sounds comfortably far off, in cosmic terms, both galaxies are essentially fated to merge. What will this titanic meeting be like? As Andromeda nears, by about 3.75 billion years from now, it will loom huge in Earth's sky, likely visible in daytime. A swirling disk of billions of stars, that begins to distort the Milky Way with its tidal pull. Eventually, the disks of the two galaxies will begin to interpenetrate. Stars from Andromeda and stars from the Milky Way will sweep past one another like intermingling bees. The night sky would become a twisted, kaleidoscopic panorama of disrupted star streams, nebula set alight by shockwaves, and new star clusters forming in droves. According to simulations, the Milky Way and Andromeda will likely pass through each other once, then maybe swing around and merge fully by around 6 or 7 billion years from now. During the interaction, our solar system is unlikely to collide with another star, but its orbit around the Milky Way could be drastically altered. It might be flung into a new region of the merged galaxy, perhaps much farther from the core than it is today. By the end of the merger, the orderly spiral patterns of both galaxies will be gone. Instead, we would find ourselves in a large, amorphous, elliptical galaxy, sometimes nicknamed Milkomeda. The merged galaxy will have a new identity, containing most of the stars from both the Milky Way and Andromeda, now sharing a common cloud of stars. Though this sounds catastrophic, it's worth noting that for any beings on individual stars, the chance of a direct stellar collision or disruption is very low. They might hardly notice the gravitational collision aside from a gradually changing night sky. The real violence is in the gas and the overall structure. And indeed, if humanity's far descendants are around, they might witness a sky ablaze with more stars and nebulae than ever as the collision triggers star formation. It would be an awe-inspiring spectacle. Galactic collisions are a crucial part of the life cycle of galaxies. Through them, galaxies grow and change form. They can rejuvenate a galaxy by kick, starting star birth, or they can quench a galaxy by using up and ejecting star, forming fuel. They create some of the most stunning vistas in the universe, luminous tails, rings, and collisional remnants that we observe with our telescopes as snapshots of different stages of this cosmic dance. In the grand scheme, collisions are also how we got from the small primitive galaxies of the early universe to the large galaxies of today. The Milky Way. Andromeda collision will be just one of countless such events that have happened throughout cosmic history and will continue to happen as time marches on. Even as the universe expands and distant galaxies recede from each other, gravitationally bound groups like our local group will eventually coalesce. The end result, far in the future, might be giant combined galaxies, each isolated in an ever-expanding void. For now, we can look at interacting galaxies elsewhere in the cosmos to understand our own galaxy's fate and the dramatic transformations collisions bring. Next, we zoom in on one of the most beautiful outcomes of galactic evolution, the process by which galaxies give birth to new stars. Whether in the wake of collisions or in the calm spiral arms, star formation is the ongoing heartbeat of a galaxy, and it's to these cosmic nurseries that we turn. The alchemy of stars, galactic nurseries, and stellar birth. Every star, including our sun, was born in a cosmic nursery, a great cloud of gas and dust within a galaxy. These nurseries, known as molecular clouds, are cold, dense patches of the interstellar medium. A typical molecular cloud might contain thousands to millions of times the mass of the sun in gas, spread over dozens or hundreds of light years. Within these dark, frigid clouds, gravity quietly begins its work. Small random density enhancements grow as gas clumps together. If a region becomes dense enough, its own gravity causes it to collapse inward. As it collapses, it fragments into smaller pockets, like a lump of dough breaking into pieces, each destined to form one or a few stars. Deep inside one of these collapsing clumps, the material compresses and heats up. A protostar takes shape, a hot, dense core of gas that isn't a true star yet, but is on its way. As the protostar gains mass from the infalling cloud, its core grows hotter and more pressurized. Eventually, When the temperature and pressure skyrocket enough, hydrogen nuclei begin to fuse into helium. This ignites the nuclear fire at the protostar's center E, and a star is born. The newfound star's radiation and stellar winds then push away the remaining shroud of gas around it, often creating a beautiful glowing nebula as the gas is ionized. What was once an opaque dark cloud now becomes a stellar nursery, lit up by its offspring. Stars tend to be born in batches. A single collapsing cloud can give birth to a whole cluster of stars, some hefty and bright, some smaller and dim. For example, peer into the Orion Nebula, a stellar nursery about 1/300 light years away. You'll see a glowing cavern of gas and dust lit by a clutch of brilliant newborn stars. Within that nebula, dozens more protostars hide in cocoons, still gathering mass. It's a snapshot of starbirth in action, a miniature version of the process unfolding countless times across our galaxy. The trapezium cluster of massive young stars at Orion's heart is carving a cavity in the cloud with intense ultraviolet light and stellar winds. Within such clusters, the most massive stars blaze to life first. Their intense radiation and powerful winds carve cavities in the cloud and can trigger further collapse in nearby parts of the cloud. In this way, massive stars can act both as catalysts and inhibitors for the next generation of stars. They are short-lived, however, living only a few million years. And when they die as supernovae, they send shockwaves through the cloud that can compress it in places and disperse it in others. In a spiral galaxy, these processes are not happening randomly everywhere, but often concentrated in the spiral arms. The spiral arms are like traffic jams in the galaxy's disk. They are regions where gas clouds get squeezed as they orbit the galactic center. When a molecular cloud enters the denser environment of an arm, it can trigger collapse and star formation. As a result, we see bright young star clusters and HII regions lining the spiral arms, marking the locations of recent star birth. These newborn stars, especially the hot blue ones, shine brilliantly but burn out quickly, so they don't drift far from their birthplaces. Hence, the arms remain defined by these ongoing nurseries. Meanwhile, older stars have had time to move away, so between the arms we mostly find middle-aged and old stars. Different galaxies have different personalities in terms of star formation. Our Milky Way currently forms only a few solar masses worth of new stars each year, quietly and steadily. In contrast, some galaxies, especially those experiencing interactions or mergers, can undergo starbursts, where dozens or even hundreds of solar masses of stars form per year. These starburst galaxies are ablaze with massive young stars, and they radiate strongly in infrared as dust in the galaxies is heated by the intense stellar newborns. Irregular dwarf galaxies can also have phases of rapid star formation, often triggered by a brush with a larger neighbor or by a fresh influx of gas. On the flip side, galaxies that have lost or exhausted their gas have virtually no new stars forming. Their stellar populations are aging without rejuvenation. Star formation is a feedback loop within a galaxy. When stars form, especially massive ones, they alter their environment dramatically. The combined effect of many massive stars in a region, through stellar winds, supernova explosions, and radiation, can create superbubbles that blow holes in the galactic gas disk, venting material out into the halo. Some of that gas may cool and rain back down to the disk later, potentially forming new clouds. Or it may escape the galaxy entirely if driven hard enough, especially in a starburst or quasar phase, an event that can effectively shut down future star formation by removing fuel. In moderate amounts, though, feedback from stars helps to regulate the pace of star formation, preventing the galaxy from turning all its gas into stars at once. Over the life of a galaxy, star formation acts as a clock and a forge. It's a clock because the rate at which gas turns into stars will determine how long a galaxy's star forming era lasts. A galaxy with a slow rate can keep making stars for tens of billions of years, while one with a rapid rate might use up its gas in only a few billion. It's a forge because each generation of stars produces heavier elements in their cores and in supernovae. Those elements get mixed into the galactic gas reservoir. Thus, the composition of the gas slowly changes. The galaxy becomes more metal-rich over time, which influences things like planet formation around new stars. In fact, our own existence is tied to this cosmic alchemy. The carbon in our cells, the calcium in our bones, the iron in our blood were all formed in previous generations of stars and scattered into the interstellar medium, eventually coalescing into the Sun and Earth. Galaxies, by forming stars, gradually enrich the cosmos with the ingredients for planets and life. Within galaxies, different environments yield different kinds of star formation. In the dense heart of a starburst or the core of a merging galaxy, star formation might be so rampant that hundreds of thousands of massive stars form in a short time, leading to an outbreak of supernovae, like a cosmic storm. In the quiet outskirts of a spiral galaxy, small clouds might occasionally birth only low, mass stars, faint red dwarfs that will live for trillions of years. Some galaxies, like large spirals, have a mix of environments, busy spiral arms and calmer inter-arm spaces, creating a balance of star formation across various scales. Other galaxies, like ellipticals, are essentially retired, containing gas that's too hot or diffuse to collapse, so star formation is dormant. From a bird's eye perspective of a galaxy, you would see star formation as twinkling patches of light. Here, a cluster of blue newborn stars. They're a glowing nebula around an emerging cluster. If you could watch in accelerated time, you'd see clouds collapse and ignite, and perhaps, after a few million years, see bubbles and blasts from supernovae shaping the surroundings. It's an endless cycle. Galaxies are constantly converting some portion of their gas into stars, which then live out their lives and return some material back to the galaxy when they die. This ongoing stellar production line is the engine that keeps a galaxy visible and vibrant. It is literally the act of galaxy building, assembling new stellar components that, for a time, light up the galaxy from within. In sum, star formation is the beating heart of a galaxy's evolution. As long as a galaxy has gas, it can give birth to stars and thus continue the cosmic story, lighting up the darkness, forging new elements, and providing the raw material for planets and potentially life. Next, we explore an enigmatic ingredient that heavily influences all these processes, yet reveals itself only through gravity: the dark matter that surrounds galaxies and shapes their fate. The hidden mass, dark matter's grip on galaxies. Galaxies are not just made of stars and gas. They are enveloped by something immense and invisible that we call dark matter. This dark matter doesn't emit light, doesn't shine or obscure like dust. It interacts with ordinary matter only through gravity, yet it profoundly influences the behavior and fate of galaxies. In fact, most of the mass in a typical galaxy is dark matter, outweighing the visible stars and gas by a factor of 5 or more. It's the hidden scaffold that holds galaxies together and connects them in the cosmic web. The first hints of dark matter's presence came from observations that didn't add up. In the 1930s, the eccentric Swiss astronomer Fritz Zwicky first proposed the existence of dark matter in 1933 after observing the motions of galaxies in the Coma cluster. He calculated that the visible galaxies didn't have nearly enough gravity to hold the cluster together. Zwicky, in his blunt style, invoked a mysterious dunkel materia, or dark matter, to explain the discrepancy. His idea was ahead of its time. It was largely dismissed or forgotten for decades. Later, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a landmark discovery after many meticulous nights at the telescope. They measured the rotation curves of spiral galaxies, essentially how fast stars and gas orbit at different distances from the galaxy's center. In a whirlpool like the solar system, we expect objects farther out to orbit more slowly because the gravity of the central mass gets weaker with distance. But Rubin found, to her astonishment, that in spiral galaxy after galaxy, the stars in the outer disks were orbiting just as fast as stars near the center. The rotation curves were flat. The expected drop off never came. This was a startling clue. If the only mass in the galaxy were the stars, gas, and dust we can see, the outer stars should not have enough gravitational pull to stay bound at such high speeds. They should drift away into space. The fact that they remain orbiting at high speed means there must be a lot of unseen mass extending well beyond the visible edge of the galaxy, creating a strong gravitational pull. The simplest explanation: an extensive halo of dark matter envelops the galaxy. This halo, roughly spherical, contains most of the galaxy's mass, though it emits no light. The stars in the outer disk are effectively orbiting within this massive invisible halo, which keeps them tethered. Dark matter halos are thought to extend far beyond the luminous parts of galaxies. For example, while the Milky Way's visible disk is about 100,000 light-years across, its dark matter halo may span 600,000 light-years or more. If we could see it, our galaxy's halo might look like a giant sphere, much larger than the Milky Way's starlit spiral, gently fading into the intergalactic medium. Every galaxy sits within such a halo, from large spirals to tiny dwarfs. In small dwarf galaxies, in fact, the dark matter's grip is often even more dominant. These little galaxies might have relatively few stars, but still plenty of dark matter, which is the only thing holding their sparse stars together. Dark matter's influence goes beyond keeping galaxies intact. It played a crucial role in galaxy formation. As described earlier, dark matter clumped into filaments and halos in the early universe, and ordinary gas fell into those gravitational wells to form galaxies. The cosmic web of large-scale structure, the immense network of galaxy clusters and filaments spanning hundreds of millions of light-years, is essentially the imprint of dark matter's distribution, with galaxies lighting up the densest spots. Without dark matter, our theories struggle to explain how the universe's structure could have formed as quickly as it did. Dark matter, being pressure, less unable to clump early, seeded galaxy formation long before normal matter could do so. Within individual galaxies, dark matter also affects their dynamics and evolution. The presence of a massive halo can stabilize a rotating disk against certain instabilities. It provides an extra gravitational well that can funnel gas towards the center or help sustain spiral density waves. When galaxies collide and merge, their dark matter halos pass through each other and overlap, adding together to form an even bigger halo around the new merged galaxy. In cluster environments, the combined dark matter of the cluster forms a deep gravitational well that can trap galaxies and super-hot gas. One of the most striking pieces of evidence for dark matter comes from images of gravitational lensing. According to Einstein's general relativity, mass bends space and thus bends light. In some massive clusters of galaxies, we see distorted, smeared images of far background galaxies, as if viewed through a funhouse mirror. These distortions allow astronomers to map the mass in the cluster. The maps show that there's far more mass than what we can see in stars and gas. A famous example is the Bullet Cluster, two colliding clusters of galaxies. In the aftermath, the X-ray emitting hot gas from each cluster was slowed and left behind at the collision center, whereas the galaxies flew on. Gravitational lensing revealed that the main mass of the clusters moved ahead with the galaxies, not with the gas, implying that the mass is dominated by something that did not collide and slow down like the gas did. This observation is a stunning confirmation that dark matter is a real physical component, separate from normal gas. Even with all this evidence, what dark matter actually is remains one of the greatest mysteries in science. We know it's there. We map its distribution. We see its gravitational effects everywhere, from the rotation of tiny dwarf galaxies to the expansion of the universe as a whole. The leading idea is that dark matter consists of some new kind of subatomic particle that doesn't interact with light, perhaps a type of particle left over from the Big Bang that swarms around galaxies. Physicists have given these hypothetical particles names like WIMPs or axions. Huge experiments deep underground and in space are attempting to detect a stray dark matter particle, and powerful colliders like the Large Hadron Collider search for hints of them. So far, dark matter particles have eluded direct detection, adding to their mystique. What we do know is that without dark matter, galaxies as we understand them wouldn't exist. Galaxies would not have formed in the same way, and those that did might not hold together. Dark matter's gravity is the glue keeping the grand design of a spiral galaxy intact and the engine that assembled galaxies in the first place. It ties entire clusters of galaxies into bound communities and delineates the cosmic web on the largest scales. In essence, dark matter is the invisible stage on which the luminous drama of stars and galaxies unfolds. We find ourselves living inside this invisible halo, unaware of its particles as they stream through us, yet deeply dependent on their gravitational presence for our very existence in a galaxy. Understanding dark matter is crucial to fully knowing galaxies, their rotation, their shape, their past, and their future. As our story of galaxies continues, we turn our attention back to the visible centers of these systems, in particular to the monsters lurking there. In the cores of galaxies, including our own, lie supermassive black holes that, when awakened, can blaze forth as active galactic nuclei and quasars, outshining entire galaxies. These extreme objects are another key piece of the galactic puzzle. Galactic beacons, quasars, and active nuclei. In the heart of almost every large galaxy lies a supermassive black hole, a gravitational titan millions or billions of times the mass of the Sun. Most of the time, these black holes are quiet, lurking in the darkness as stars and gas orbit innocently around them. But when a black hole feeds, a galaxy can transform. Matter swirling into a hungry black hole releases astonishing energy, enough to outshine the entire galaxy. The nucleus of the galaxy blazes with light, and we call it an active galactic nucleus. When an AGN is extremely luminous, especially seen in the distant universe, we often use the term quasar. A quasar is essentially a hyperactive galactic core E, a supermassive black hole gorging on infalling gas and shining like a beacon across the cosmos. How does a black hole, which by itself emits no light, produce such brilliance? The key is the accretion disk, a swirling disk of gas and dust that forms around the black hole as material falls in. As matter spirals inward, immense gravitational and frictional forces heat the disk to incredible temperatures, millions of degrees. The disk begins to glow fiercely in X-rays, ultraviolet, and visible light. Gas closer in moves at relativistic speeds, magnetic fields twist through the disk, and often the black hole's spin and magnetic forces channel some of the inflowing material into twin jets that shoot out along the black hole's poles. These jets are streams of charged particles accelerated to nearly the speed of light, blasting out of the galaxy's core into space. They can extend thousands or even millions of light years, creating radio, emitting lobes far outside the galaxy. To an observer from afar, a galaxy with an active nucleus might appear as a bright star, like point at its center, or even completely outshine the galaxy's entire starlight. Quasars in the distant universe appear as brilliant beacons on the sky, some of the brightest individual objects known. For instance, a typical quasar can emit hundreds or thousands of times more light than a normal galaxy containing 100 billion stars. And all that energy comes from a region no larger than our solar system, the area right around the black hole. It's as if a flashlight the size of a pinhead outshone a lighthouse. That's the power of a feeding supermassive black hole. Quasars were first identified in the 1960s as puzzling sources of radio waves and faint, star-like optical counterparts with strange emission lines. When astronomer Martin Schmidt realized those lines were highly redshifted hydrogen, it meant these objects were incredibly distant, yet astonishingly bright. This was the first clue that quasars were not stars in our own galaxy, but something far more powerful in the distant universe. We now know thousands of quasars, and we interpret them as galaxies in an active phase. Their central black holes are accreting matter at a high rate. Quasars were more common in the early universe, which makes sense. Back then, galaxies had more gas in their centers and were colliding more frequently, providing ample fuel for black holes. Many quasars lived during that cosmic era when galaxies were growing and merging. Today, with less fuel available, most big galaxies have quiescent black holes. Our Milky Way's central black hole, for example, is currently a feeble glimmer by quasar standards. It occasionally snaps up a passing chunk of material, producing a flicker of X-rays, but nothing like a continuous blaze. Active galactic nuclei come in a menagerie of types: quasars, blazars, Seyfert galaxies, radio galaxies, which largely reflect different viewing angles and power levels of the same basic phenomenon. If we look directly down the barrel of a jet, we see a blazar. If the active nucleus is powerful, but we see it at an angle where the galaxy's dust obscures some light, we might categorize it as a radio galaxy or a type of Seyfert galaxy. But all these are AGNs, central engines powered by accretion onto supermassive black holes. The effects of a quasar or AGN on its host galaxy are profound. The radiation and winds from the active nucleus can blast apart or heat the gas in the galaxy's core. A vigorous quasar can effectively quench star formation in its host by blowing away or heating the cold gas. This means that a galaxy's active heart can govern its own growth, a kind of self-regulating mechanism. If too much gas piles into the center, the black hole lights up, the quasar blows out gas, and the galaxy's star, forming future, is altered. This feedback might explain why we observe the tight correlation between black hole mass and the bulge mass of galaxies. They grew in tandem, each affecting the other. Observationally, an active galaxy can look quite spectacular. Some galaxies have bright cores and jet structures visible in radio or optical images. In images from Hubble or James Webb, we sometimes see quasars with faint galactic hosts around them, or pairs of interacting galaxies where one nucleus is lit up, possibly triggered by the interaction. When we peer into the distant universe, almost every speck of light in the Hubble ultra-deep field that isn't a star in our Milky Way is a quasar shining from an era long ago. The existence of quasars tells us that galaxies and their black holes are intimately connected. A galaxy might spend a small fraction of its life as a quasar, but during that time, it can have an outsized influence on its surroundings and be visible clear across the universe. In a sense, quasars are cosmic lighthouses, marking where massive black holes dine. They allow us to study galaxies in the making, as many quasars are seen in young, formative galaxies undergoing collisions or rapid growth. They also serve as backlights. We can study the gas in the space between galaxies by looking at how quasar light filters through it. Our Milky Way's black hole might one day gulp enough material to become more active, though it likely would never rival the brightest quasars from the universe's youth. Still, even a modest AGN can produce spectacular phenomena like X-ray flares or relativistic jets. The center of our galaxy shows evidence of past active episodes, gigantic bubble structures emanating from the core, perhaps from an AGN flare a few million years ago. In the grand tapestry of galactic life, quasars represent a youthful exuberance, a time when a galaxy's central engine can dominate its light output. They are a phase that many galaxies likely went through. Today, by studying both gentle galaxies and those with raging quasars, we get a complete picture of galactic evolution. We see a galaxy's quiet, star, forming suburbs, and also its volatile, energetic core when it turns on. With the phenomenon of AGN understood, we can now appreciate that a galaxy is not just a collection of stars drifting passively. It has a central heart that can beat furiously when fed. Having explored the brilliant hearts of galaxies, we now step back out to consider something smaller, yet still crucial to the galactic story: the dwarf galaxies that swarm around larger ones and fill the universe. These diminutive galaxies may be tiny, but they carry clues about how galaxies form and about the mysterious dark matter, making them far more important than their size suggests. Little brothers, dwarf galaxies and galactic satellites. Surrounding every large galaxy are smaller satellite galaxies, dwarf galaxies, the diminutive companions that populate the universe in huge numbers. Dwarf galaxies are tiny by galactic standards, perhaps only a few thousand light years across or less, containing as few as a few million stars. They come in various flavors. Some are irregular clumps with ongoing star formation. Others are diffuse spheroids of old stars. Though they may seem insignificant next to a giant spiral or elliptical, these little galaxies play an outsized role in the story of cosmic evolution. In our own cosmic neighborhood, the Milky Way has dozens of known dwarf satellites. The two most famous are the large and small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye in the southern hemisphere. These clouds are actively forming stars, with visible nebulae like the Tarantula Nebula in the Large Cloud, a colossal star birth region. They orbit our Milky Way and are in the process of being gradually disrupted. A stream of gas, the Magellanic Stream, stretches behind them, torn off by our galaxy's gravity and the ram pressure of halo gas. In a few billion years, the Magellanic Clouds will likely merge into the Milky Way, adding their stars to our own. Besides these prominent examples, the Milky Way is encircled by many dwarf spheroidal galaxies, much smaller, fainter objects like Sagittarius, Draco, Ursa Minor, and Fornax. These tend to have little to no gas and consist mostly of ancient, faint stars. They often appear as just a sparse scattering of stars, detectable only with long exposures on large telescopes. The Sagittarius dwarf is actually in the process of being devoured by the Milky Way right now. It has been stretched into a long stream of stars, wrapping around our galaxy. Over time, its stars will assimilate into the Milky Way's halo. Each of these tiny galaxies is like a fossil record of the early universe. Many of them formed their stars more than 10 billion years ago and haven't done much since, preserving a snapshot of conditions shortly after galaxies began to form. Dwarf galaxies are incredibly valuable to astronomers as laboratories for dark matter and galaxy formation. They are the most dark matter-dominated galaxies known. In some ultra-faint dwarf galaxies, the few thousand stars move under the influence of a dark matter halo that outweighs them by hundreds or thousands of times. One extreme case is Segway 1, a diminutive Milky Way satellite so faint it has only a few hundred stars, yet they are held together by a blob of dark matter roughly 600,000 times the Sun's mass. That means Segway 1's mass is almost entirely dark matter, with a barely detectable glimmer of starlight. Measurements of star motions in tiny galaxies like Segway 1 or Triangulum 2 suggest that these systems might have up to 1,000 times more mass in dark matter than in stars. It's as if each faint dwarf is mostly a ball of dark matter with a sprinkling of stars. This makes them excellent testbeds for dark matter theories. How does dark matter cluster on small scales? Are the number of dwarf galaxies we see consistent with predictions from cosmological models? At first, there was a missing satellite problem. Computer simulations of cosmic structure predicted that a Milky Way-sized halo should have hundreds of smaller sub-halos orbiting it, potential dwarf galaxies. Yet for a long time we had observed only a few dozen around the Milky Way. Where were the rest? In the past 2 decades, however, New ultra-faint dwarf galaxies have been discovered in droves. The count of Milky Way satellites has climbed substantially, and we now suspect many more await detection, lurking in the shadows with extremely few stars. It seems that many dark matter sub-halos did form, but most of them failed to produce many stars, likely because the cosmic reionization heated and stripped gas from the smallest protogalaxies. Star formation in those puny halos was stifled, rendering them effectively dark. The ones we do see are the slightly bigger or luckier halos that manage to form stars despite these harsh conditions. The dwarfs that do shine provide crucial checks on our cosmological models. Their distribution around the Milky Way, their orbits, and their internal properties all carry information about how our galaxy were assembled. For instance, studies find that many of the Milky Way's dwarf satellites lie in a somewhat flattened arrangement, a feature still debated and potentially telling us something about past interactions or the filamentary nature of how they were acquired. The star formation histories of dwarfs also vary. Some, like the Magellanic Clouds, still form stars today. Others, like the dwarf spheroidals, formed most of their stars early and then stopped. Environment is a factor. Dwarfs near a big galaxy often lose their gas and thus cease making new stars, while isolated dwarfs farther away can retain gas longer. Dwarf galaxies are thought to be the building blocks of larger galaxies in the hierarchical model of cosmology. Over billions of years, small protogalaxies merged to build big ones. Essentially, today's large galaxies are the result of many past dwarf galaxy collisions and mergers. In our Milky Way's halo, astronomers identify remnants of several dwarf mergers beyond just Sagittarius. These show up as stellar streams or distinct groups of stars with common origins. The globular clusters orbiting our galaxy may include some that were originally brought in by dwarfs. In Andromeda, our nearest large neighbor, the halo is even more populated with substructures and streams, evidence of a rich history of consuming smaller companions. Dwarfs also affect their parent galaxies in subtle ways. A satellite can tug on the primary galaxy via gravity. For example, the Large Magellanic Cloud is massive enough that it's pulling on our galaxy, causing both to move toward their common center of mass. Interactions between a dwarf and a large galaxy can create disturbances. The Milky Way's disk has ripples and warps, possibly induced by past encounters with satellites. And when a dwarf with fresh gas orbits a big galaxy, it can funnel gas into the big galaxy's halo, which may later rain down and fuel future star formation in the main galaxy. Thus, dwarfs can be providers of material, not just victims. They might extend the star, forming life of a big galaxy by donating gas during their infall. Because of their small size, dwarf galaxies also highlight the thresholds and extremes of galaxy formation. They exist in regimes where a single burst of star formation can exhaust their supply or blow out what's left. Some dwarfs show evidence of one ancient burst and then long quiescence. Others, in isolation, might have sporadic bursts separated by many millions of years as gas slowly pools in again. Some tiny galaxies may have been completely stunted by the ionizing glare of the first stars and quasars during reionization, never forming many stars at all. They remind us that not all galaxies are the continuously rotating, long-lived star factories like the Milky Way. Some are stop and go, some are one and done, and everything in between. In summary, dwarf galaxies may be small, but they are crucial pieces of the cosmic puzzle. They were the first galaxies to form, the building blocks that merged into larger ones. They are the most common galaxies by number. They are reservoirs of dark matter, offering evidence for its behavior on small scales. And as satellites, they are constantly interacting with larger galaxies, being pulled apart, contributing gas and stars, and generally complicating the life of their big hosts. In their diminutive form, dwarfs carry outsized importance for understanding gravity, dark matter, and the history of galaxy assembly. Having explored these miniature galaxies, we now widen our perspective to the enormous patterns that galaxies themselves form on the grandest scales. Just as stars gather into galaxies, galaxies congregate into clusters, superclusters, and filaments in a vast cosmic web. It's time to venture into the large-scale structure of the universe, the architecture of galaxies on cosmic scales. The cosmic web, clusters, superclusters, and filaments. Galaxies, including the Milky Way, are not scattered randomly through space. They often gather in larger structures bound by gravity. On the first rung of this cosmic ladder are galaxy groups. A galaxy group generally holds a few dozen or fewer galaxies. The Milky Way and Andromeda, along with the dozens of dwarf galaxies orbiting them, form the local group, a collection of more than 50 galaxies spanning about 10 million light-years. Our local group is a typical small cluster. It has two dominant spirals, a third spiral, and many dwarfs. The galaxies in the local group orbit their common center of gravity and are bound together. Step up in scale, and we find galaxy clusters. These are much larger assemblies, containing anywhere from hundreds to thousands of galaxies, all bound in a single gravitational swarm. Galaxy clusters are among the most massive coherent structures in the universe. A good example is the Virgo cluster, the nearest sizable cluster, roughly 50 million light-years away in the direction of the constellation Virgo. It holds over 1,000 galaxies in a volume a few million light-years across. The cluster's core is crowded with elliptical galaxies, including a giant central galaxy sitting at the center, feasting on smaller galaxies that venture too close. Clusters like Virgo are permeated by a hot X-ray, emitting gas that fills the space between galaxies. This intracluster gas actually outweighs all the stars in the cluster, and dark matter outweighs both. Clusters are dark matter, dominated just like galaxies, but on a larger scale. The galaxies in a cluster move at hundreds or even over 1,000 kilometers per second, ricocheting through the cluster's deep gravitational well. Clusters themselves aren't isolated. They often lie in larger complexes called superclusters. A supercluster is essentially a cluster of clusters, an extended grouping of galaxies, groups, and clusters spanning perhaps a few hundred million light-years. Our local group, for instance, is on the outskirts of the Virgo supercluster, which contains the Virgo cluster and dozens of other groups and clusters in our corner of the universe. In recent years, astronomers have realized that what we used to call the Virgo supercluster is part of an even larger complex named Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster, as mapped by the flow of galaxies, includes the Virgo cluster, the Hydra, Centaurus supercluster, and other clusters, all linked by gravity. It stretches over 500 million light-years and contains the mass of perhaps 100,000 galaxies. At the center of Laniakea is a gravitational focal point dubbed the Great Attractor, a region of space causing a peculiar motion of our local group and others toward it. This Great Attractor's pull is part of the evidence of Laniakea's extent. Connecting these clusters and superclusters are the filaments, long strings of galaxies and galaxy clusters, tens to hundreds of millions of light-years long, but relatively thin. Between the filaments lie voids, enormous regions with very few galaxies, sometimes tens of millions of light-years across where only a handful of galaxies dwell. One famous void, the Boötes void, is about 330 million light-years in diameter and contains very little. It's been whimsically described as a spherical space with nothing in it, though in reality there are a few galaxies scattered within. The contrast between filaments and voids gives the universe a kind of foamy texture. Some filaments can join together into sheet, like structures or walls. For example, the Sloan Great Wall, identified in large galaxy surveys, is a massive thread of galaxies and clusters, about 1.5 billion light-years long. among the largest structures ever observed. The cosmic web's appearance is often compared to a sponge or foamy bubbles, concentrations of matter surrounding vast empty voids, or even to the brain's neural networks on a cosmic scale. This arrangement, clusters, superclusters, filaments, and voids, is what we call the cosmic web. It formed from the same primordial fluctuations we discussed earlier, amplified by gravity over cosmic time. Dark matter played the key role. It clumped into filaments early, and ordinary matter followed, flowing into those gravitational channels to form galaxies. The result is that on the grandest scales, matter in the universe is arranged in twisting, thread-like structures with immense voids in between. When we run large computer simulations of the universe, starting from the initial conditions of the Big Bang and letting gravity draw matter together, a filamentary pattern naturally emerges. The simulation's output, when compared to maps of real galaxies from surveys like the Sloan Digital Sky Survey, is strikingly similar. It's one of the triumphs of modern cosmology. The cosmic web we observe is exactly what our theories predict given dark matter and the expanding universe. To give a sense of scale, an individual galaxy might be 100,000 light years across, a cluster 10 million, a supercluster 200 million, the distance between major superclusters on the order of 1 billion light years. The observable universe is about 93 billion light years in diameter. On those largest scales, the cosmic web starts to blend into homogeneity. An extremely large cube of the universe would contain a statistically even mix of galaxies and voids. But up to those enormous scales, the web is evident. It's breathtaking to realize that the Milky Way, with all its hundreds of billions of stars, is but a single point on the vast cosmic web, a node in a structure so immense it defies full comprehension. In a thought experiment, imagine pulling back your vantage point. Zoom out from our solar system, past the Milky Way's disk, until our whole galaxy is just a glowing spiral among others. Zoom further, and the Milky Way and its neighbors blend into the local group, a small cluster of galaxies. Pull back more, the local group becomes just one clump in the Virgo cluster. Further still, the Virgo cluster and adjacent groups merge into the Laniakea supercluster, a great flowing concentration of matter. Finally, as you zoom to a view hundreds of millions of light years across, the superclusters themselves line up as filaments, the cosmic web revealed in its entirety, galaxies like grains of dust, tracing the grand design of gravity. This mental journey underscores how nested our existence is within ever grander systems. We live within this web. Our Milky Way, Andromeda, and neighbors float together in the local group, which is being gently pulled as part of the Virgo Laniakea supercluster along a filament towards the Virgo cluster. In far, far future billions of years, that journey might bring our remnants into Virgo's embrace. When we peer out at the night sky, the stars we see with the naked eye all belong to our own galaxy, but the faint smudges we see through telescopes are all part of this grand structure. For instance, the Coma cluster of galaxies appears as a dim patch in the constellation Coma Berenices, but it is the heart of a rich filament connected to other clusters. The Shapley supercluster, one of the most massive supercluster concentrations known, is another knot in the web observable in southern skies. The cosmic web is not just a backdrop, it influences how galaxies evolve. Galaxies in clusters are different from those alone in the field. They tend to be redder and gas poor, partly due to interactions and the hot cluster environment stripping their gas. Galaxies riding along thin filaments can funnel towards clusters, often getting processed by smaller group environments before entering a cluster. Thus, a galaxy's larger scale environment plays a role in its story, illustrating the adage, location, 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 on a cosmic scale. It's remarkable to think that barely 100 years have passed since we even confirmed galaxies outside the Milky Way. Now, with our arsenal of observations and simulations, we have mapped the architecture of the universe on the largest scales. We have, in essence, discovered the blueprint of creation's vast cosmic web. Having charted out this grand design, we turn to some of the most puzzling denizens of this landscape, galaxies that challenge our definitions, those that are extremely diffuse or even seemingly made mostly of dark matter with hardly any stars. These ultra, diffuse and dark galaxies push the boundaries of what a galaxy can be, and exploring them will deepen our insight into the unseen components of the universe. Ghostly galaxies, ultra, diffuse and dark galaxies. Not all galaxies are the bright, well-defined islands of stars we might imagine. In recent years, astronomers have discovered a class of galaxies so faint and spread out that they've been called ultra, diffuse galaxies, ghostly apparitions barely visible against the night sky. These galaxies can be as large in extent as the Milky Way, yet have only a tiny fraction of the stars. Picture a galaxy with the diameter of a giant spiral, but the total luminosity of a dwarf galaxy, effectively a huge puff of stars so sparse that if you lived inside it, you might not realize you were in a galaxy at all, because the stars would be so few and far between. One example that made headlines is Dragonfly 44, a faint galaxy in the Coma cluster. When first studied, Dragonfly 44 appeared to have about the mass of the Milky Way, but only about 1% of the number of stars, implying it was 99% dark matter by mass. It was dubbed a failed galaxy, or a dark matter galaxy, as if it started forming like a normal large galaxy, but somehow failed to produce many stars. Dragonfly 44 also sports an unusually rich system of globular clusters for its luminosity, supporting the idea that it once had the potential to be a big, star-filled galaxy, but didn't follow through. This and other UDGs beg the question, how do you get a galaxy that big with so few stars? There are several ideas. One is that these UDGs formed in high-spin halos. The gas was spread out over a larger area and thus never condensed into the dense concentrations needed for prolific star formation, resulting in an oversized but dim galaxy. Another idea is tidal heating. Perhaps they were once normal galaxies that got puffed up by gravitational tides in a cluster environment, stretching them out and thinning their star distribution. Some might be failed giant galaxies. Their dark matter halo and initial gas were like that of a large galaxy, but something prevented normal star formation. What remained is a dim shadow of a galaxy, mostly dark matter, holding a thin sprinkling of stars. On the other extreme of the spectrum are reports of galaxies that seem to have very little dark matter at all. In 2018, astronomers announced the discovery of a galaxy named NGC 1052, DF2, that defied expectations. This diffuse galaxy, about the size of a dwarf, appeared to have so few stars that one would expect it to be dominated by dark matter, yet the velocities of those stars were so low that they implied the galaxy's mass was nearly all accounted for by the visible stars. In other words, it seemed to lack the unseen mass that every other galaxy its size needed. A year later, a second galaxy in the same group, DF4, was found with similarly anomalous properties. These no-dark matter galaxies caused a flurry of both excitement and skepticism. If true, they would be the first galaxies discovered that contradict the rule that galaxies form within dark matter halos. Could it be that dark matter can be stripped entirely from a galaxy, leaving behind a wraith of stars? Or might there be an alternative explanation? One possibility is that these galaxies did form in normal dark matter halos, but later experienced a gravitational interaction that sheared away most of their dark matter. For example, if DF2 and DF4 passed very close to a much larger galaxy, the tidal forces could have pulled out a large fraction of their dark matter and outer stars, leaving behind an inner core of stars with little surrounding halo. Another clue DF2 and DF4 both have unusual populations of globular clusters, fewer in number, but unusually luminous for the galaxy's size. This might hint that something about their formation was atypical. Some later studies argued the distance to these galaxies might have been overestimated initially. If they are a bit closer than first thought, then they have fewer stars, and the original no dark matter conclusion may soften. The jury is still out, but most scientists suspect these galaxies aren't truly dark, matter-free, but rather odd products of interactions. Important nonetheless, because they show how far interactions can go in reshaping a galaxy. When we say dark galaxies, we could also mean the purely hypothetical objects made almost entirely of dark matter, with virtually no stars at all. Our cosmological models predict that there should be many small dark matter halos that failed to form stars. These would be completely invisible to us, except through gravitational effects. Detecting one directly is extremely challenging. How do you see an object that emits no light? One strategy is via 21 pound-centimeter radio surveys of hydrogen gas. Astronomers have searched for isolated clouds of hydrogen, with motions indicating they are held together by some mass, yet with no visible stars, essentially a dark galaxy candidate. A few candidates have been reported. One famous one, discovered in the Virgo cluster, was a large cloud of hydrogen that some thought might be a dark galaxy. However, skepticism remains, as it's hard to distinguish a truly dark galaxy from tidal debris. So far, no incontrovertible 100% dark galaxy has been confirmed. But the hunt itself is telling. If we found even one, it would confirm that starless galaxies can exist and would be a direct piece of evidence for the prevalence of dark matter halos without baryons. What do these ghostly galaxies tell us? For one, they underscore the complex interplay of matter in galaxies. We have galaxies like ultra, diffuse ones that are heavily dominated by dark matter, and perhaps others that are so dominated by normal matter that they barely show dark matter's presence. This diversity challenges our understanding of galaxy formation. Our theories have to accommodate both ends of this spectrum. They also serve as natural experiments. For example, a galaxy lacking dark matter would be a huge test for alternative theories of gravity, which predict you can't have one without the other. Conversely, galaxies with extreme dark matter dominance test our models of star formation efficiency. Why did they form so few stars relative to their dark mass? Ultra, diffuse galaxies also likely hint at the role of environment. The fact that many UDGs are found in clusters suggests that environment, e.g. interactions with other galaxies or the cluster's tidal field, might be responsible for their puffed-up nature. They might be the blown out remains of formerly normal galaxies that got their gas removed early and their structures distended. In less dense environments, such fragile, puffy galaxies might not survive. The cluster both creates them and, ironically, helps preserve them by confining them in its gravitational embrace. As we continue exploring these extreme galaxies, we sharpen our understanding of the thresholds of galaxy formation. We learn what it takes for a dark matter halo to actually light up with stars, and what circumstances can prevent it. We see how galaxies can be stripped to the bone by interactions, and how nature can produce objects that challenge the very definition of a galaxy. After all, a galaxy has traditionally been defined as a gravitationally bound collection of stars. But what do we call a gravitationally bound collection of mostly dark matter and almost no stars? Or conversely, a tenuous collection of stars that seems to have shed its dark matter? These edge cases blur the lines, forcing us to refine our definitions. The mysteries of ultra, diffuse and dark galaxies remind us that there is still much to learn about the invisible scaffolding of the cosmos. With new telescopes and surveys, we are now better equipped to find more of these phantom galaxies and unravel their stories. Each such discovery is like finding an unexpected creature in the cosmic wilderness, challenging what we thought galaxies could or couldn't be. After exploring the extremes of galactic forms, from the magnificent to the barely, we return now to the grand perspective of the universe. We've spoken of countless galaxies, but how many can we actually see? How far does our vision reach? Next, we'll discuss the observable universe, how deep our telescopes peer into the cosmic past, how many galaxies likely populate our universe, and what lies at the edge of our sight. The observable universe, counting galaxies and reaching back in time. Our journey through the cosmos has taken us from our own Milky Way to the farthest reaches of galactic existence. One naturally wonders, how many galaxies are there? And how far can we see into the depths of space and time? The truth is both humbling and exhilarating. When the Hubble Space Telescope pointed its lens at what seemed to be an empty patch of sky in 1995 for 10 days, the resulting image, the Hubble Deep Field, revealed thousands of galaxies of all shapes and colors packed into that tiny speck of sky. This was followed by the Hubble Ultra Deep Field in 2004, an even longer exposure that unveiled nearly 10,000 galaxies in an area of the sky only a fraction of the moon's apparent size. Every swirl, blob, and smear in those deep images was an entire galaxy, some as they were over 13 billion years ago. Extrapolating these results to the whole sky suggested that the observable universe contains on the order of hundreds of billions of galaxies. For a long time, a common estimate was around 200 billion galaxies in the observable universe. But even that might be an underestimate. In 2016, using data from new surveys and some clever modeling, astronomers proposed that there could be as many as 1-2 trillion galaxies in the observable universe. Many of those would be very small, faint galaxies, the kind that current telescopes can't easily see, especially those that existed in the early epochs of the universe. It's sobering to realize that every time you look at a clear night sky, the few thousand stars you see belong to our Milky Way. Yet overhead, invisible to our eyes, are billions upon billions of other galaxies, each with its own stars, planets, and perhaps life, scattered across the universe. The phrase observable universe is key. It refers to the portion of the universe from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old and space has been expanding, the current radius of the observable universe is about 46 billion light years. That encompasses an immense volume. Think of a sphere centered on Earth that includes all galaxies, whose light has traveled 13.8 billion years or less to get here. Galaxies beyond that horizon are simply too far for their light to have ever reached Earth in the age of the universe. They may exist, but we cannot see them, and they cannot see us. How far have we seen? With the Hubble Space Telescope, we detected galaxies at around 13.3 billion years back time. One example was a galaxy nicknamed GN-Z11, observed in Hubble's deep surveys at a redshift of about 11. That was a record for some years. Now, thanks to the James Webb Space Telescope, we've pushed the frontier even closer to the dawn of galaxies. In 2022-2023, JWST identified galaxies with tentative redshifts of 13, 14, even up to around 16, if confirmed. Those correspond to times just 250-300 million years after the Big Bang. We are likely seeing the flicker of some of the first generations of galaxies that formed in the universe. These farthest galaxies are tiny and primordial, looking often irregular agglomerations of stars, blazing with the light of massive newborn stars, but relatively low in mass. They lack the heavier elements that subsequent generations of stars would build up. Observing them is like peering back in time to watch the universe's infancy, the cosmic dawn, when the first galaxies and quasars burst into light and began reionizing the fog of hydrogen that filled space after the Big Bang. Each new leap in telescope power effectively extends our time machine further. JWST is now letting us study in detail the era when the very first galaxies took shape. So, how many of those galaxies can we actually see? In practice, even with our best telescopes, we cannot see all the hundreds of billions of galaxies out there. Many are too faint or too redshifted. But we can see an astonishing variety. From the grand spirals a few million light years away, to ancient red ellipticals in distant clusters billions of light years away, to tiny blue specks that are infant galaxies in the early universe. As telescopes improve, our observable catalogue of galaxies grows. The upcoming Vera C. Rubin Observatory will map billions of galaxies across the sky, though mostly relatively nearer ones. Space telescopes like JWST and the planned Nancy Grace Roman Space Telescope will focus on finding and analyzing the faint distant ones. What does this reveal about the universe's timeline? By surveying galaxies at different distances, we can trace the evolution of galaxies over cosmic time. We see that in the early universe, galaxies were generally smaller, more irregular, and forming stars at a furious rate. Many were clumping together and merging. As time went on, small galaxies combined into larger ones, star formation peaked, and then gradually declined. Galaxies in the more recent universe often appear larger, more mature, with well-defined structures like spiral disks or big diffuse ellipticals, and many have slowed their star formation. By looking as far back as JWST allows, we're trying to witness the moment when the very first stars and galaxies ended the cosmic dark ages. We also glean the universe's timeline from the most distant light of all, the cosmic microwave background. This is not a galaxy, but the faint remnant glow of the Big Bang itself, released about 380,000 years after the Big Bang, when the hot plasma cooled enough for atoms to form and light to travel freely. The CMB comes to us from every direction, a nearly uniform background with tiny fluctuations that encode the seeds of future galaxies and clusters. It represents the absolute limit of what we can see via electromagnetic radiation. Beyond that, the universe was opaque. It's like a foggy wall at the edge of our vision. We cannot see through the CMB with light. It's the backdrop of the observable universe. Thus, our observations currently span from the present day all the way back to those first few 100 million years, when the earliest galaxies and black holes were turning on, and finally to the CMB wall at 13.8 billion years ago. Each big telescope and survey has effectively peeled back another layer of the universe's history. Our picture of the cosmos's timeline has grown rich. We have seen the universe as a baby, as a rambunctious toddler, as a vigorous youth, and in its middle age. As for how many galaxies exist in total, the number is truly mind-boggling and might ultimately be unanswerable if the universe is infinite. But in the observable volume we inhabit, current best estimates suggest on the order of 1 trillion galaxies. It's a number so large it loses meaning. Suffice it to say, there are more galaxies in the observable universe than there are stars in any individual galaxy. Looking up at a dark sky, one might feel that the universe is mostly empty darkness sprinkled with stars. But thanks to our instruments, we know the opposite is true. The darkness is filled with the light of galaxies, stretching to the edge of what is knowable. Standing here, on a small planet within the Milky Way, we have managed to gauge the universe's extent and populate it with galaxies by the billions. This achievement of human curiosity sets the stage for our final reflections on what it means to live in a universe so vast and full of galaxies, to be made of the stuff of stars, and to contemplate it all from our tiny corner of the cosmic ocean. Eyes on the cosmos, telescopes that revolutionized our view. Our understanding of galaxies has expanded hand in hand with the advancement of our telescopes, our eyes on the universe. Even before the space age, giant ground-based telescopes pushed our galactic knowledge. The 100-inch Hooker telescope on Mount Wilson in the 1920s allowed Edwin Hubble to measure galaxies' distances and the expansion of the universe. The 200-inch Hale telescope at Palomar was the world's largest for decades. It revealed exquisite details in galaxies and allowed astronomers in 1963 to identify the first quasar, realizing it was an unbelievably distant powerhouse. Each leap in technology has brought a leap in knowledge. In particular, a few key instruments and missions have transformed our view of galaxies in ways earlier astronomers could only dream of. The Hubble Space Telescope, launched in 1990, has been often called one of the most productive scientific instruments ever built. Above the blurring effect of Earth's atmosphere, Hubble has provided crystal, clear images of galaxies near and far. It showed us spiral galaxies in unprecedented detail, glittering arms and delicate dust lanes, and peered into the cores of ellipticals to find evidence of central black holes. Hubble's most famous contribution might be its deep field observations. By staring at empty patches of sky for days, HST captured the Hubble Deep Field and Ultra Deep Field, revealing a rich backdrop of galaxies stretching to the horizon of the universe. These images fundamentally changed our perception. Every tiny patch of sky, if you look long enough, is teeming with galaxies. Hubble also provided distance measurements via Cepheid variables and supernovae that helped nail down the scale of the universe and the rate of its expansion. Its crisp images of galaxy collisions, gravitational lensing arcs, and proto-galactic fragments have filled textbooks and our collective imagination. If Hubble opened a clear window in visible light, the James Webb Space Telescope, launched at the end of 2021, has opened a new window into the infrared universe. Galaxies emit light across the spectrum, and by looking in the infrared JWST, can see through dust clouds that obscure stellar nurseries and detect the faint glow of extremely distant galaxies whose light has been stretched into the infrared by the expanding universe. In its first years of operation, JWST has already identified some of the earliest galaxies ever observed, spotted rich organic chemistry in galaxy gas clouds, and produced stunningly detailed images of galaxies like never before. JWST's ultra-sensitive infrared vision is giving us a direct look at the cosmic dawn, complementing Hubble's view of the later universe. Together, Hubble and Webb act like time machines, Hubble mapping the middle epochs and Webb pushing toward the beginning. Beyond these two famous space telescopes, there have been and are many other missions that significantly advanced galactic astronomy. Radio telescopes. In the mid-20th century, radio dishes like those at Jodrell Bank and later the Very Large Array in New Mexico started mapping radio emission from galaxies. They discovered jets and lobes emanating from active galactic nuclei. Radio surveys found quasars before we knew what they were. Bright radio sources with star-like optical counterparts that turned out to be distant AGNs. Today, radio telescopes like ALMA can detect the cold molecular gas in galaxies, billions of light years away, revealing where future stars will form and how galaxies acquire fuel. They also measure the rotation of outer gas in galaxies to chart out dark matter distributions. Interferometric radio images of colliding galaxy clusters have even detected the shock waves of cluster mergers and the halo radio glow from cosmic ray electrons in cluster-scale magnetic fields. X-ray observatories, space-based. X-ray telescopes, such as Chandra and XMM, Newton, have shown us the high-energy side of galaxies. They map the X-ray glow of hot gas in galaxy clusters, providing direct measurements of cluster masses. Chandra's sharp vision revealed how clusters collide. X-ray images of galaxies show the halo of hot plasma that many galaxies, especially ellipticals, sit in, and pinpoint the light from accreting black holes at galactic centers or ultraluminous X-ray binaries sprinkled throughout galaxies. X-ray surveys also discovered mysterious diffuse X-ray backgrounds and contributed to the discovery of intergalactic filaments of warm, hot gas connecting clusters. infrared and UV surveys. Before JWST, we had Spitzer, which, though smaller, detected countless dusty stars, forming galaxies, and helped uncover ultra-luminous infrared galaxies. Spitzer observed high, redshift galaxies in infrared too, bridging some of the gap until JWST. In the ultraviolet, the Galactic Space Telescope mapped UV emission across the sky, highlighting where in galaxies young massive stars are concentrated. Galactic's pictures of spirals showed hazy UV halos of star formation and star streams, and captured starburst activity in dwarfs and interacting galaxies. Ground-based surveys and upcoming telescopes, the Sloan Digital Sky Survey, starting in the 2000s, used a dedicated 2.5-meter telescope to perform an immense imaging and spectroscopic survey of galaxies. SDSS gave us a 3D map of over 1 million galaxies, which led to the discovery of large-scale structures, like the cosmic web filaments, and refined our understanding of galaxy demographics. The forthcoming Vera C. Rubin Observatory in Chile will take this further, imaging the entire visible sky to great depth repeatedly and capturing billions of galaxies and their changes over time. The Nancy Grace Roman Space Telescope will conduct wide field surveys at near infrared, providing a Hubble-like clarity, but on areas of sky hundreds of times larger, ideal for finding distant galaxies and mapping dark matter via weak gravitational lensing. And on the ground, the new extremely large telescopes will, later this decade, give astronomers unprecedented power to study faint galaxies and directly image features in galaxies tens of millions of light years away that currently appear as mere smudges. They'll also dissect the light of very distant galaxies into spectra to determine their compositions and internal motions in detail, complementing Webb's work with brute force light, gathering, and sharp resolution. Each of these tools, whether in space or on the ground, has peeled back a layer of the cosmic onion, bringing galaxies into better focus. Our toolkit now spans the full electromagnetic spectrum: radio, microwave, infrared, optical, ultraviolet, X-rays, and gamma rays. By combining all these views, we get a holistic picture of galaxies that was impossible a century ago. It's remarkable to think that barely a lifetime ago, we didn't even know other galaxies existed. Now, with our Hubbles and Webbs and myriad other instruments, we routinely catalogue galaxies, billions of light, years distant, capture images of their shapes, break their light into spectra to gauge their compositions and star formation rates, and even watch as they collide or as their cores light up as quasars. Missions like Hubble and Webb stand as milestones in this ongoing journey, each bringing the universe's galaxies closer to us. As we consider these powerful tools and the discoveries they have enabled, we prepare to leave the domain of scientific observation and enter a more introspective realm. With the data gathered by these instruments, we can now reflect on what it means to live inside a galaxy, to be made of stars, and to find our place in cosmic time. In the final section, we'll step back from the technical and immerse ourselves in the philosophical and existential implications of knowing that we are part of a universe filled with galaxies. Reflections. Our place among the galaxies. On a warm, clear night, if you find yourself far from city lights, you can see the Milky Way arching overhead, a milky band of light splashed across the sky. That soft glow is the combined shine of billions of distant stars in our home galaxy, seen from within. We live inside a galaxy embedded about 26,000 light years from the Milky Way's center, orbiting with our sun and planets among the spiral arms. For most of human history, we didn't know that we were inside a galaxy, or even what a galaxy was. Now, in the light of all we've learned, think about what that means. It means that when you gaze up at the Milky Way, you are seeing the structure of our galaxy from the inside, the disk of stars and nebulae in which our Sun is just one modest member. It means that our Sun is one of perhaps 400 billion stars in the Milky Way, and our Milky Way is one of perhaps 1 trillion galaxies in the observable universe. Our Earth is a tiny world circling a garden, variety star, in the outskirts of one galaxy, among uncountable others. This realization can make one feel incredibly small. The scales are almost too vast to hold in the mind. The distance to even the nearest major galaxy, Andromeda, is 2.5 million light years, so far that the light hitting your eye tonight from Andromeda left that galaxy when early human ancestors were just beginning to make stone tools. And yet, consider the flip side. Though we are tiny, we are also a part of this grand universe. We are made of it. The iron in your blood, the calcium in your bones, the oxygen you breathe, those atoms were forged long ago in stars, likely in the Milky Way, during stellar alchemy and violent supernova explosions. We are made of stuff, the products of galactic recycling. Over the history of our galaxy, generations of stars lived and died, each enriching the cosmic clouds with heavier elements, which eventually found their way into the gas that formed our Sun, our planet, and ultimately us. In a very literal sense, the galaxy is in our bodies. We are the universe, in a small way, contemplating itself. As one philosopher, scientist mused, we are a way for the universe to know itself. Atoms with curiosity, as someone once said. From our vantage point on Earth, we've managed to decipher the Milky Way's structure, learn the history of galaxies, and even map the large-scale cosmic web. Feats of understanding accomplished by a clever species of primate using telescopes and mathematics. It's astonishing. The universe became aware of itself through us. We, tiny and fragile, can mentally span billions of light, years and billions of years, reconstructing events and structures we will never physically touch. When we look at a picture of a distant galaxy, we're seeing a piece of the universe's autobiography, a chapter from a time and place utterly remote, yet connected to us through the simple act of a photon of light traveling across space and landing in a telescope mirror. To live inside a galaxy is to be both extremely insignificant and extremely special. Insignificant because the galaxy does not notice us. The Milky Way would be essentially unchanged if our solar system vanished tomorrow. We occupy no central role. The universe is not arranged with us in mind. But special because despite that, we have the unique gift of consciousness to appreciate the cosmos. The stars in the Milky Way burn on obliviously, yet here on a rocky planet around one star, the atoms assembled into beings that can admire the beauty of a spiral galaxy, that can feel awe at the sight of the Milky Way's shimmering band, that can wonder about the possibility of other minds in those other galaxies doing the same. We have, in a sense, imbued the galaxy with meaning simply by being here to observe it. Galactic timescales stretch far beyond human lifetimes. Our solar system orbits the galaxy every 230 million years, making one galactic year. A human life is a mere instant by that clock. In fact, when dinosaurs roamed the Earth, it was roughly one galactic year ago. In one sense, that might make our lives feel vanishingly short, but it also means that life on Earth is tied into the dynamic life of galaxies. Civilizations might rise and fall while galaxies perform their slow gravitational dance. Perhaps in some distant future, beings will witness the night sky dramatically change as the Milky Way merges with Andromeda. None of us will see that, but knowing it will happen connects us to the far future and to the long narrative of our galaxy. When confronting these immensities, it's natural to ask, what do galaxies mean for us? They can make our everyday concerns feel small, the petty squabbles, the borders we draw on our tiny planet. Viewed against the cosmic backdrop, such things seem trivial. Many astronauts, after seeing Earth from space against the void, report a profound overview effect, a shift in perspective, recognizing the unity and fragility of life on our pale blue dot. A similar effect comes from the cosmic perspective, recognizing that all humanity shares one tiny home galaxy, that we have far more in common with each other than any difference, and that our true tribe is as large as the Earth, perhaps even as large as the Milky Way. We are all voyagers together through the galaxy. There is also a deep comfort and inspiration in this perspective. The atoms that make us have endured across billions of years and multiple galaxies' journeys. They will persist long after we are gone, possibly incorporated into new living beings or new worlds when our sun's time is over. We are part of something continuous and far bigger than ourselves. The light we make, radio waves carrying our broadcasts, for instance, is even now leaving the Milky Way and traveling into intergalactic space. In that sense, a piece of us will touch other galaxies, albeit faintly. Knowing about galaxies also invites a profound humility. We inhabit a universe where the dramatic and the sublime are commonplace. Galaxies crash together, black holes light up as quasars, stars are born and die in colorful nebulae. Entire clusters of galaxies dance in gravity's grip. Against such a backdrop, the significance we assign to our own achievements or struggles finds a healthy perspective. But rather than make us feel despair at our smallness, this awareness can instill a sense of gratitude and wonder. Out of all the possibilities, we have the privilege to witness and understand a slice of the universe's story. Finally, consider that for most of history, the galaxies were unknown to us. Only in the last century have we recognized what the spiral nebulae truly are. In that short time, essentially a couple of human lifetimes, we've gone from not even knowing other galaxies exist to mapping the cosmos and decoding the light from the dawn of time. This rapid progress shows something powerful. Our desire to learn is as expansive as the universe itself. We are a curious, bold species, unafraid to ask big questions. What is that hazy band in the sky? What are those faint smudges in the telescope? How did we come to be? And remarkably, we've been able to answer many of them. As we conclude the story of galaxies, we find that it is deeply intertwined with our own story. Galaxies are not just distant objects. In a very real way, they are our extended homes. The Milky Way gave birth to the Sun and Earth. Galaxies provided the raw materials for life and the stage for every cosmic event that led to our existence. When we marvel at the galaxies, we are in a sense marveling at our origins. And we are fortunate to live at a time when we can see them, eons from now. The expansion of the universe will carry many galaxies beyond our observable reach, potentially leaving future civilizations more isolated. We, however, inhabit a cosmic epoch rich with galaxies to observe and learn from. So, the next time you find yourself under a truly dark sky, allow yourself a moment of communion with the Milky Way. Think of the myriad stars you see and know that you are connected to them, that you are made of their fire, that your existence is tied to their past. Think of the countless galaxies beyond, each with its own wonders and perhaps its own watchers. Feel the swell of awe that comes from realizing you are part of a cosmos so vast and magnificent. In that feeling lies something profoundly human and profoundly beautiful. A sense of belonging to the universe. A star dies. For a brief moment it outshines everything around it, a beacon of unimaginable brilliance piercing the void. What was once a steady pinprick of light in the night sky suddenly blossoms into a furious brightness, only to fade away and vanish. This is the paradox of a supernova, the explosive death of a star that looks to us like the appearance of a new one. In that instant of violent death, something new is born in its wake. We watch from our tiny world with both wonder and humility. Across the gulf of light, years, a distant sun has reached the end of its life and unleashed an energy beyond comprehension. It is an end in the most dramatic fashion possible, a final act that illuminates the cosmos. Yet it is also a beginning, The star's death throes scatter the heavy elements forged in its heart out into space, seeding the darkness with the ingredients for new stars, new planets, perhaps new life. In dying, the star becomes a cosmic phoenix. Its ashes enrich the galaxy and fertilize the universe. In a supernova's fleeting flash, we witness a cycle as old as the cosmos itself, creation and destruction entwined. The universe began with light, and in each stellar death, there is a small echo of that beginning, a burst of radiance, a flood of particles and atoms hurled outward to partake in future creations. Every one of us carries the story of these explosions in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe. Those atoms were forged in stellar furnaces and scattered by stellar explosions long before the Earth coalesced. We are, quite literally, made of stardust, born from the remnants of ancient supernovae. So when we look up at the night sky, we are not just seeing stars, we are seeing memories. Each point of light is a story that may one day end in a supernova, as countless stars have before. Some of those stories ended eons ago, their light only now reaching us, bearing news of cosmic endings that were also cosmic beginnings. In the darkness between the stars, there are ghosts, expanding clouds of gas and dust that were once suns. And there are futures, nascent stars, forming in nebulae enriched by those past explosions. This is the tale of supernovas, at once an elegy and a celebration. It is the tale of how stars live, die, and transform the universe. It is a story written across millions of years, but observable in a single human lifetime as a sudden blaze in the sky. Together, we will journey through this story. We will witness the birth of a star and follow its life to the cataclysmic moment when the core collapses. We will explore the different kinds of supernovae that nature has devised and see how these brilliant events have touched human lives and imaginations throughout history. We will visit the most famous stellar explosions known to science and what they left behind. Beautiful nebulae, spinning neutron stars, perhaps even black holes that swallow all light. As we voyage through time and space in our collective imagination, we will see how supernovas are not random acts of destruction, but essential threads in the fabric of the cosmos. They are beacons, guiding our understanding of distant galaxies, engines driving the evolution of those galaxies, and perhaps harbingers of danger in our own cosmic neighborhood. They are the universe's great alchemists, forging heavy elements and sewing them far and wide. And in their afterglow, we find insight into the deepest mysteries of existence, including our own origins. Let us begin at the beginning of a star's life. Because to understand the death of a star, we must first understand how it lives. In the cosmic theater, every death scene is set by the long life that came before it. And so we step back to watch a star being born, knowing that in its birth lie the seeds of its demise and the promise of everything that will follow. The life cycle of stars. Before a star can die, it must live. Our journey begins in a vast, cold cloud of gas and dust, drifting in the galactic night, a stellar nursery waiting for a spark. In these dark, silent nebulas, gravity gradually draws denser clumps together. We imagine ourselves floating there as one particular clump, maybe a little larger than the rest, starts to collapse under its own weight. As it compresses, it heats up and begins to glow with a faint reddish light. We have witnessed the birth of a protostar, the first flicker of a new sun. In time, the growing protostar's core becomes hot and pressurized enough to ignite nuclear fusion. When its central temperature climbs to tens of millions of degrees, hydrogen atoms begin fusing into helium. With that first flash of fusion fire, a true star is born. It stabilizes, entering the long, steady middle of its life known as the main sequence. For millions to billions of years, this young star will shine, a blazing sphere of plasma held up against gravity, by the continuous energy of fusion. In this stage, a delicate balance is struck. The inward pull of gravity and the outward push of radiant heat are in equilibrium. The star has found its rhythm, a stable heartbeat in the darkness. We look around and see countless stars on the main sequence, each with its own life clock ticking at a different rate. The massive ones, dozens of times heavier than our sun, burn their fuel extravagantly and live fast, shining hot and blue, white. They may spend only a few million years in this stable phase. Smaller stars, like our sun, burn more moderately and can shine for tens of billions of years. And the tiniest red dwarfs, barely heavy enough to ignite fusion, sip their fuel so slowly that they could outlive galaxies, trillions of years into the future. A star's mass is its fate. It determines how luminous the star is and how long it will live. As the eons pass, even the most enduring stars exhaust their primary fuel. In the core of a middle-aged star, like our sun, the hydrogen that once fused so plentifully is gradually converted to helium. When the core fuel runs low, the star begins to change. We watch as our once stable star starts to swell and redden, transforming into a red giant. Its outer layers puff outward, cooling and glowing a deep sunset hue. In its core, new fusion reactions ignite as helium fuses into carbon and oxygen. For a while, the star finds a new balance, but it is precarious, a sign of old age. For a star of modest size, this red giant phase is the prelude to a quiet death. When the helium is finally spent, such a star cannot muster the temperatures needed to fuse heavier elements. The core, now a hot ball of carbon and oxygen ash, begins to contract, while the outer layers become unstable. Gently, at least by cosmic standards, the star sheds its outer envelope into space, creating a glowing shell of gas called a planetary nebula. What remains at the center is the star's tiny, exposed heart, a white dwarf, no bigger than Earth, made of degenerate matter and slowly cooling over eternity. This is one possible end of the stellar life cycle, a hushed fading rather than a cataclysm. The once grand star becomes a faint ember, and the beautiful planetary nebula disperses into the interstellar medium over tens of thousands of years. But our focus is on a far more dramatic finale, one reserved for the giants among stars. Let us rewind a bit and follow the life of a truly massive star, say 10 or 20 times the mass of the Sun. These behemoths blaze blue, white, and live brief, brilliant lives. They race through their fuel, shining millions of times brighter than the Sun, and expending their core hydrogen in mere millions of years. When hydrogen runs out, the transition is anything but gentle. The core contracts and heats rapidly, and the star balloons into a red supergiant, enormous enough to engulf entire planetary systems. Betelgeuse, the red shoulder of Orion, is one such star nearing this final act, bloated, unstable, and nearing the end of its supplies. Inside such a red supergiant, the core temperatures soar high enough to fuse helium into carbon and oxygen, and then, with frightening speed, to fuse those elements into heavier ones. The star's life accelerates toward its conclusion. In successive stages, carbon burns to neon and magnesium, neon burns to oxygen, oxygen to silicon, and silicon to iron. We imagine peering into the heart of this titanic star in its last million years and seeing something like the layers of an onion, concentric shells of burning elements, hydrogen in the outer layers, then helium, carbon, oxygen, and so on, all feeding an increasingly ferocious furnace at the core. At last, the star builds an iron core deep in its center. Iron is a fatal milestone for a massive star, for when nuclei fuse into iron, no energy is released. The process that sustained the star's outward pressure grinds to a halt, as if a beating heart has suddenly stopped. The core can no longer support the crushing weight of the star's immense outer layers. For a brief moment, a tense silence falls inside the star, the calm before an unimaginable storm. This is the end of the star's life as a normal star. In the iron core, which may be about the size of Earth, but with over 1 billion times Earth's mass, no more thermonuclear miracles remain to stave off gravity. The star has reached the brink of catastrophe. All the glorious millions of years of shining have led to this precipice. The outward light falters, the balance is undone, and gravity prepares to exact its final victory. In that final moment, the stage is set for a collapse and an explosion, the supernova we have been waiting for. The life cycle of the star, from birth in a nebula to maturity in the main sequence to bloated old age, has brought it inexorably to an existential crisis. What happens next will be the subject of the following chapter in our story. A chapter written in fire and fury as the star's core collapses and a supernova is born. The final act, core collapse. The end comes swiftly and without mercy. In the heart of our massive star, the iron core has grown to a critical mass, roughly 1.5 times the mass of our Sun, compressed into a sphere barely 50 miles across. At this extreme, the familiar laws of matter are on the verge of breaking down. Gravity, long held at bay by the energy from fusion, finally has the upper hand. And then, in a fraction of a second, the core buckles. We find ourselves in the core at the moment of collapse. Temperatures have soared to over 10 billion degrees and rising. The iron nuclei, pressed unbearably tight, begin to disintegrate into smaller particles. Electrons are driven into protons, turning them into neutrons and releasing floods of ghost, like particles called neutrinos. The core's atoms, once the powerhouse of the star, are now crushed into an ultra-dense ball of neutrons. In the span of a heartbeat, the core implodes, matter-free, falling inward at speeds approaching a significant fraction of light. The densities reach astronomical levels, higher than those inside an atomic nucleus. For an instant, the core is like a giant atomic nucleus itself, a sphere of neutrons about the size of a city. Suddenly, this collapse slams to a halt. The neutron core, essentially incompressible, resists further squeezing. It's as if the star has hit a concrete floor at nearly 1/4 the speed of light. The infalling material recoils. In that violent rebound, a powerful shockwave is born at the core and begins plowing outward through the star. But the shock alone is not yet the famous supernova explosion. It threatens to stall as it loses energy, tearing apart iron nuclei in its path. For a brief moment, it seems the star might simply collapse and swallow itself quietly. Then something extraordinary intervenes. The flood of neutrinos. Remember those neutrinos produced as electrons and protons were crushed together? In the turmoil of the collapsing core, billions upon billions of neutrinos are streaming out. Normally, neutrinos hardly ever interact with matter. They can zip through an entire star as if it were empty space. But here, in the densest environment the universe can offer outside of a black hole, even neutrinos begin to collide with matter. They deposit a stupendous amount of energy into the infalling layers just behind the shock front. This energy is the spark that revives the dying shockwave. With neutrino power added to the rebound, the shock roars back to life, surging outward with renewed fury. Now the star truly explodes. Within less than a second, the core collapse has transformed into an outgoing detonation. The shockwave tears through the star's layers from inside out. The overlying material, hydrogen, helium, carbon, all the way to the surface, is blasted into space at incredible speeds. The pressures and temperatures are so immense that new nuclear reactions ignite in the chaos, forging elements heavier than iron in fleeting moments of neutron bombardment. Gold, uranium, and dozens of other heavy elements are synthesized in these last violent seconds, like the final flourish of a master craftsman finishing a grand work. From outside, we would see nothing of this cataclysmic ballet until the shock breaks the star's surface. One moment, the star was a red supergiant. perhaps shining a bit erratically. The next moment, boom. The surface of the star is abruptly ejected, and a brilliant flash of light known as the shock breakout occurs. The star's outer layers, now unleashed, race outward as an expanding fireball, glowing a hot blue, white from the immense heat of the explosion. Within hours, the brightness swells dramatically. Within days, the exploded star becomes one of the brightest objects in its galaxy. A supernova has appeared where a familiar star used to be. At the core of this expanding fury lies the crushed remnant of the star, the ball of neutrons that survived the collapse. It is extremely small and dense. If its mass is below a certain threshold, it will settle as a neutron star, a city-sized stellar corpse. If it's more massive, nothing can halt its collapse, and it continues shrinking to become a black hole, an abyss from which no light escapes. But in either case, that core is no longer producing light. All the radiance of the supernova comes from the explosion's aftermath, from radioactive isotopes created in the blast decaying and heating the debris, and from the shock heating the star's outer layers as they expand. The dying star's final scream echoes across the electromagnetic spectrum. First comes a burst of neutrinos, an invisible herald racing ahead of the light. Then, the light arrives, rapidly growing to a peak brightness that can rival an entire galaxy's output of stars. For weeks, too, months, the debris of the star glows intensely, powered by the decay of unstable isotopes forged in the fireball. We imagine watching from a safe distance as the shattered star's remains expand in a great spherical shell, cooling and dimming over time. Where once there was a mighty star, now there is a cloud of glowing ash, the embryonic form of a supernova remnant, and, hidden at the center, a compact new child of the cosmos born from the core's collapse. This is a core collapse supernova, the fate of massive stars. It is nature's grandest light show, a release of energy so colossal that for a short time, a single star's death outshines all the billions of stars in its galaxy. But not all supernovae follow this script. There is another type of stellar death, one that begins not with a massive living star, but with the quiet ember of a star that died long ago. Before exploring the remnants and outcomes of core collapse explosions further, we will take a detour to understand the other path to a supernova, the path of the white dwarf and the thermonuclear runaway. Two paths to destruction, Type 1 versus Type 2. Not all stars that go supernova do so in the same way. As astronomers studied the light from these stellar explosions, they found telltale differences. Some supernovae show signatures of hydrogen in their exploded debris. Others have no hydrogen lines at all. This was the first clue that there are two distinct paths to stellar oblivion. In the astronomical naming convention, those with hydrogen are called Type 2 supernovae, and those without are Type 1. We now understand that behind these spectral differences lie very different stories. The Type 2 supernova is the scenario we have just witnessed, the core collapse of a massive star that still had its hydrogen envelope at the time of explosion. The ejected material in a Type 2 supernova's spectrum reveals abundant hydrogen because the star was a red supergiant until the moment it died. These are the deaths of solitary massive stars, tearing themselves apart from the inside out. But what of the Type 1, the ones that mysteriously lack hydrogen? It turns out some stars die by borrowing a kind of second life, and then blowing themselves to pieces in a thermonuclear fury. Imagine a star, much like our Sun. After living out its life and quietly shedding its outer layers, it ends as a white dwarf, a small, dense stellar corpse composed mostly of carbon and oxygen, with no ongoing fusion. Normally, a white dwarf simply cools over the eons, but if this white dwarf has a close companion star, fate may have a more explosive plan. Picture a binary star system where one star is a white dwarf and the other is a living star. The white dwarf, though dead in the sense of fusion, still exerts strong gravity. It begins siphoning gas from its companion, pulling hydrogen and helium off the neighboring star's outer layers. The stolen gas accumulates on the white dwarf's surface, compressing and heating. For a while, this theft goes unnoticed on a cosmic scale. The white dwarf grows more massive, creeping toward a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. This is the maximum mass that a white dwarf, supported only by the quantum pressure of electrons, can hold without collapsing. When the white dwarf approaches this threshold, something incredible happens. The pressure and temperature at its center become high enough to ignite carbon fusion in a runaway manner. Unlike a normal star, the white dwarf has no way to regulate this burning. It is essentially a giant bomb waiting for a spark. The carbon fusion spreads rapidly in a wave through the dwarf's interior, unleashing a titanic thermonuclear explosion. In a fraction of a second, the entire white dwarf is obliterated in one of the most brilliant fireworks the universe has to offer, a Type Ia supernova. This Type Ia supernova is fundamentally different from the core, collapse Type II. It is not a star's core imploding under gravity. It is a prompt detonation, a nuclear bomb on a stellar scale. The white dwarf is entirely destroyed. No neutron star or black hole is left behind, only an expanding cloud of debris. Because the explosion comes from the sudden fusion of about a sun's mass of carbon and oxygen, it tends to produce a very consistent brightness each time. In fact, Type Ia supernovae act as standard candles for astronomers. Since they all reach roughly the same peak luminosity, we can gauge their distances by how bright they appear. We'll revisit this idea later when we see how such supernovae helped map the universe. For now, consider what the lack of hydrogen in the Type I spectrum means. A white dwarf has no hydrogen envelope. It lost all that long ago when its progenitor star shed its outer layers. So when it explodes, the debris shows no hydrogen lines. That's how we know a supernova was likely a Type Ia. Its light is missing hydrogen and often shows a distinctive signature of iron and nickel from the burned outcore of the white dwarf. There are also other subclasses of Type I. For instance, Type Ib and Type Ic supernovae are actually massive star explosions like Type II, but ones that shed their outer hydrogen before exploding. These usually happen in massive stars that blew off their envelopes via strong winds or interactions in a binary system, leaving a bare core to collapse. Thus, they are core collapse supernovae like Type II, only stripped of their outer layers, so they masquerade as Type I by lacking hydrogen in their spectra. It can sound alphabet, soup confusing, but the essence is this. One path to supernova is a single, massive star collapsing under gravity. The other path is a smaller star, a white dwarf, blowing itself apart in a nuclear runaway. Both paths produce immense explosions, but their causes and outcomes differ. In one, a stellar core implodes and might leave a dense remnant. In the other, a stellar remnant detonates and leaves nothing substantial behind at its center. Understanding these two fundamental types gives us insight into the variety of cosmic fireworks we observe. Some supernovae announce the dramatic death of a lone giant. Others signal the demise of a long dead star, reignited by a companion. Together, Type I and Type II supernovae account for nearly all the stellar explosions we see lighting up distant galaxies. With this framework in mind, we can better appreciate the events and remnants we are about to explore. Now let us step out of the theoretical realm and into human history. Long before we unraveled the astrophysical mechanisms, people witnessed supernovae in the sky without knowing what they were. They saw brilliant new stars appear where none had been before and grappled with their own interpretations. Our cosmic story now crosses paths with the human story as we look at supernovas through the eyes of those who saw them from Earth centuries ago. Supernovas in human history. Long before modern science unraveled the physics of supernovae, humans were witnessing these celestial events with naked eyes and recording their wonder and fear. To ancient sky watchers, the sudden appearance of a brilliant new star in the firmament was an astounding, often ominous event. The regular stars and planets followed known patterns, but a new star, a nova or guest star as some called it, defied the idea of an unchanging heaven. It was as if the cosmos itself had spoken in a burst of light. One of the earliest recorded supernovae occurred in 185 AD. Chinese astronomers noted a strange guest star in the southern sky. It lingered for about 8 months before fading away, enough time for ancient observers to take careful notice. They dutifully recorded its position and its disappearance in official court chronicles. We now know that this was indeed a supernova, and modern astronomers have rediscovered the faint traces of its remnant about 8,000 light years from Earth. That ancient record, largely qualitative and couched in the language of omens, aligns with the physical evidence we see today of a Type Ia supernova explosion that occurred nearly 2 millennia ago. In late April of the year 1006 AD, a staggeringly bright guest star exploded into Earth's skies in the constellation Lupus. It ultimately reached an estimated visual magnitude of around 7.5, so bright that it was visible during the day. Observers across Eurasia marveled at it. Historical records say it cast shadows at night and was even visible during the day. The Egyptian astronomer Ali ibn Ridwan wrote that it was a large star which appeared in the south, having an enormous luster, far outshining Venus. We believe this was the brightest supernova ever observed by humanity in recorded history, what we now call SN 1006. People all over the world took note, and in some places it stirred fear or was interpreted as a portent. In North America, a possible record exists in an ancestral Puebloan pictograph, a depiction of a star next to a crescent moon on a rock wall in Chaco Canyon, which some have interpreted as a representation of this guest star. Though intriguing, such interpretations remain debated. Just a few decades after that, on July 4th, 1054 AD, all of Earth was treated to celestial fireworks as another new star appeared, this time in the constellation Taurus, the Bull. Chinese court astronomers recorded that it was initially brighter than the moon and lingered in the sky for nearly 2 years before slowly fading from view. Unbeknownst to those observers, they were watching the birth of what we today call the Crab Nebula, the expanding remains of that exploded star. SN 1054 was likely a massive star's death. The memory of this event may also have been preserved outside East Asia. Medieval Japanese and Arabic records also mention a brilliant guest star around that time. And as mentioned, some interpret the rock art in the American Southwest as depicting the event. For medieval Europe, knowledge of these events was sparse. Europe in 1006 and 1054 was in the middle of the Dark Ages and early medieval period, and scholarly astronomy was less developed than in the Islamic world or China. Moreover, Aristotelian doctrine held sway. The heavens beyond the moon were thought to be immutable and unchanging. A bright new star did not fit that worldview and might even have been ignored or explained away by those who adhered to the idea of perfect, unchanging skies. Still, by the Renaissance a few centuries later, careful observers were starting to challenge that ancient dogma. In November 1572, sky watchers in Europe, including a young Danish astronomer named Tycho Brahe, were astonished by a brilliant star in the constellation Cassiopeia, where no star had been seen before. Tycho diligently observed this novastella every night, measuring its position relative to the fixed stars. He found it showed no parallax, meaning it was far beyond the moon, out among the stars, which directly contradicted Aristotle's notion of an unchanging celestial realm. Tycho's supernova shone as bright as Venus for weeks. We now suspect SN 1572 was a Type Ia thermonuclear supernova, the kind involving a white dwarf. Modern studies of the remnant show no neutron star at the center, consistent with a type Ia where the star was obliterated. For Tycho and his contemporaries, the event was pivotal. His observations, published in a work titled De Nova Stello, were a key piece of evidence that the heavens do change, helping pave the way for the new astronomy of Copernicus, Galileo, and Kepler. To the public and religious authorities, the new star was often seen as an omen. To Tycho, it was a scientific revelation. Only 32 years later, in October 1604, another brilliant star burst forth, this time in the constellation Ophiuchus. The famous astronomer Johannes Kepler observed it closely and wrote a book about it. SN 1604, or Kepler's supernova, became brighter than all stars and planets in the sky at its peak. Like Tycho's, it had no measurable parallax, further driving the nail into the coffin of the Aristotelian crystalline spheres theory. It was the last supernova observed in our Milky Way with the naked eye. Modern astronomers have studied Kepler's supernova remnant and, based on its characteristics, believe it too was likely a type Ia event. Thus, the two great Renaissance supernovae were both thermonuclear explosions of white dwarfs, yet their appearance at critical moments in history had enormous impact on human thought, marking the end of an era when the cosmos was thought to be static and perfect. Throughout human history, only a handful of these new stars have been recorded, but each left an imprint on culture and science. From Chinese astrologers linking them to dynastic fortunes, to European scholars using them to question classical doctrines, supernovae have occasionally influenced the course of human thought. Most of the time, the stars live and die unseen. But when one does announce itself to us, it rarely goes unnoticed. These events also gradually built a bridge between myth and science. Each recorded observation, from 185 AD to 1572 to 1604, added a piece to the puzzle that modern astrophysicists would later assemble with telescopes and physics. Today, we can return to those historical supernovae with our scientific tools. The Crab Nebula still glows in our telescopes, and at its center, a pulsar, a rapidly spinning neutron star, blinks 30 times a second, the collapsed core left from that explosion. The remnants of Tycho's 1572 and Kepler's 1604 supernovae have been detected as expanding shockwaves in space, and careful measurements of their light, echoes, and debris composition have helped identify their type. In this way, the observations of long-ago sky watchers connect directly to the science we conduct now. The people of the past saw supernovas without understanding their true nature, but they carefully noted their appearance and timing. We, following in their footsteps, can point our instruments to those same locations centuries later to learn the why and how. It is a beautiful continuity of curiosity. Now, with the historical context in mind, let's focus on a few of those famous supernovae that have become legends in both astronomy and culture. The ones whose names have been mentioned, the mysterious guest star of 1054 that created the Crab Nebula, the brilliant new stars observed by Tycho and Kepler that altered the course of astronomy, and a much more recent stellar explosion that heralded the dawn of a new era in space observation. These are supernovas that stand out like beacons in human history's record of the sky. Witnessing great explosions, famous supernovas. Across the ages, certain supernova events stand out as especially notable, either for their brilliance, for the insights they gave us, or for the lore that surrounds them. Let us revisit a selection of these cosmic spectacles in more detail, to feel what it might have been like to witness them and to understand what they have taught us. SN 1054, the Crab Nebula's birth. It is summer in the year 1054. On a July night, people around the world gaze upward to find a startling new light in the heavens, near the starry outline of Taurus the Bull. Chinese astronomers in the Song dynasty record that it is as bright as Jupiter, eventually even brighter, visible in the daytime for weeks. They call it a guest star and note its gradual fading over nearly 2 years. What those observers see is the death of a massive star, roughly 6,500 light years away. Today, when we point a telescope at that same spot, we see the Crab Nebula, a sprawling tapestry of filamentary gas and dust expanding in space. At its center, a tiny pulsar flashes 30 times a second like a cosmic lighthouse. This pulsar is the collapsed core of the star that exploded. The Crab Nebula, with its eerie tendrils of glowing gas, is essentially frozen fireworks from 1054, still expanding at thousands of kilometers per second. Studying it across different wavelengths has given astronomers invaluable insight into how supernova debris evolves and how neutron stars behave. One can imagine the awe of ancient sky, watchers seeing the initial explosion, not knowing that before them was the creation of a beautiful nebula that later astronomers would come to understand and marvel over. The Crab Nebula stands as a bridge between human history and astrophysics, a guest star turned enduring monument in the sky. Tycho's star of 1572. Fast forward to November 1572, Denmark. Tycho Brahe, returning from his evening walk, looks up and is astonished to see a brilliant star in the otherwise familiar pattern of Cassiopeia. A star that simply was not there the night before now shines proudly. Tycho quickly organizes systematic observations, measuring the star's position relative to the moon and known stars night after night. He finds, to his wonder and intellectual delight, that the new star exhibits no parallax, no shift against the distant star background from Earth's orbit. It must lie among the fixed stars, far beyond the moon, proving the heavens are not immutable. Tycho writes about this discovery in detail. The star shines with the brightness of Venus, then slowly fades over about 16 months. We now know SN 1572 was a Type Ia supernova, a thermonuclear explosion of a white dwarf star in a binary system. Its remnant, seen with modern telescopes, is an expanding cloud of gas with no pulsar or neutron star inside. Tycho's careful work on this supernova provided crucial evidence that the Aristotelian cosmos was flawed. It marked a paradigm shift. The universe beyond Earth was dynamic and changing. Culturally, Tycho's new star challenged theologians and philosophers. Scientifically, it propelled the likes of Kepler and Galileo to further question cosmic dogma. It is poignant that a dying star, which had likely been dead for thousands of years before its light reached Earth, helped spark the birth of modern astronomy. Kepler's supernova of 1604. Just 32 years after Tycho's event, the cosmos provided another spectacular display. In October 1604, in the constellation Ophiuchus, a new star blazed forth. It reached magnitude 2.5, outshining every star and planet in the night sky. The great mathematician and astronomer Johannes Kepler observed it extensively. People across Europe saw it. Kepler, much like Tycho, found that it showed no parallax. By this time, the Copernican view of the solar system was gaining traction, and Galileo would soon turn a telescope to the heavens. Kepler's supernova, though a brilliant apparition, was the last such to be observed in our Milky Way to date. Modern analysis of its remnant, using space telescopes, indicates it was likely a Type Ia as well. Kepler compiled observations of the 1604 supernova, noting its color changes and steady decline in brightness over a year and a half. Kepler's work, published in De Stella Nova, along with Tycho's earlier nova, cemented the idea that the heavens evolve. Philosophically, it shook the last resistance to the notion that change and decay occur in the celestial realm just as on Earth. After Kepler's star, no new stars were seen in our galaxy, so these two Renaissance supernovae stand out as heralds of a new worldview. They bookend the 16th century's scientific revolution and each bears the name of the astronomer who studied it because their observations were so influential. Supernova 1987A, a modern spectacle. For more than 300 years after Kepler's 1604 event, no supernova bright enough to see with the naked eye was observed, though many undoubtedly occurred hidden behind interstellar dust or on the far side of the galaxy. Then, on February 24, 1987, something historic occurred. A brilliant new star was spotted in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible to the naked eye in the southern hemisphere. This was the nearest supernova since Kepler's about 168,000 light-years away. Supernova 1987A was extraordinary, not just for being visible to modern humans, but for being studied with modern scientific tools. Prior to the visible light, detectors deep underground in Japan, the US, and the Soviet Union picked up a flurry of neutrinos, 24 neutrinos in total, arriving within a 13th of a second window, just hours before the supernova was seen. These ghostly particles were emitted from the collapsing core of the star and provided direct confirmation of the core collapse mechanism we described. It was the first time humanity caught neutrinos from beyond the solar system, and they came from a dying star's core. When the light arrived, telescopes around the world and above it turned to watch SN 1987A. They saw the rise and fall of its light, measured the nuclear isotopes powering its glow, and observed its debris expanding. SN 1987A turned out to be a bit of a surprise to theorists. The star that exploded was not a red supergiant, but a blue supergiant, a hotter, more compact star. It had likely been a red supergiant earlier, but perhaps merged with a companion or shed mass in a complex way that left it blue at the time of collapse. The star left behind a striking arrangement of glowing rings, material it had ejected in earlier epochs, which the supernova's blast wave has since been colliding with, producing a fireworks show of its own as the rings brighten in response. We are still observing 1987A decades later. It's a living laboratory for supernova physics. So far, no neutron star has been definitively seen inside, leaving a tiny bit of mystery. But we detected the cobalt and titanium produced in the explosion, confirming models of how elements are forged. We witnessed the light from the blast echo off interstellar dust, giving us different perspectives of the event. In short, 1987A was like an astrophysical Rosetta Stone, offering answers to long-standing questions and posing new ones. For people around the world in 1987, especially those in places like Australia or Chile, who could see the Large Magellanic Cloud in their night sky, the appearance of a new star was thrilling. Unlike in 1572, it didn't spark fear or philosophical crisis. Instead, it sparked celebration among astronomers and curiosity among the public. At observatories, champagne bottles were uncorked when the first neutrinos were confirmed and the optical counterpart was found. Humanity had waited centuries to see such an event up close, and now we finally had front row seats. SN 1987A inaugurated the era of multi-messenger astronomy, using not just light, but particles like neutrinos to study cosmic events. And it came just as computing and telescope technology allowed us to capture it in unprecedented detail. From the ancient guest star of 1054, recorded by Chinese astrologers, to the modern supernova of 1987, observed with neutrino detectors and space telescopes, our understanding has grown immensely. Each famous supernova has left an enduring legacy. The Crab Nebula's pulsar confirmed the existence of neutron stars. Tycho's and Kepler's observations helped dismantle the old cosmic order. SN 1987A gave direct confirmation of theory and a wealth of data on how supernovae work. They are shining milestones on our journey to comprehend the universe. Having witnessed what happens when stars explode, we turn now to one of the most profound consequences of these events: the creation of the very stuff that makes up planets and people. In the violent cauldrons of supernovae, elements are forged that otherwise would not exist. This is the story of nucleosynthesis, the cosmic alchemy carried out in stellar life and death. Stardust and elements, nucleosynthesis in supernovae. Every atom in our bodies has a story that stretches back to the stars. The golden ring on a finger, the calcium in our bones, the iron in our blood, all were forged in cosmic furnaces and explosive crucibles. Supernovae are not merely spectacular light shows, they are also the universe's great alchemists. To understand how, we must look at what happens deep inside stars and during those final explosive moments of their deaths. Throughout a massive star's life, its core is a fusion factory, sequentially forging heavier elements out of lighter ones. Hydrogen fuses into helium in the star's youth. Later, helium burns into carbon and oxygen. Then, in truly massive stars, oxygen, neon, magnesium, silicon, sulfur, and more in turn undergo fusion as the star approaches old age. This sequence of fusion reactions builds up the periodic table within the star, but it stops at iron. As we saw, once iron accumulates in the core, no further fusion can release energy. Without energy output to support it, the iron core succumbs to gravity and collapses, triggering a core collapse supernova. When a supernova explosion occurs, it not only liberates these pre-made elements by blowing the star apart, it also creates new ones in the heat of the blast. Consider the core, collapse supernova of a massive star. As the shockwave rips through the star's layers, the extreme heat and flood of neutrons trigger a flurry of nuclear reactions in the surrounding material. In mere seconds, elements heavier than iron are synthesized via rapid neutron capture (E), a process called the R process. The collapsing core unleashes an enormous number of neutrons, and atoms riding the shockwave absorb these neutrons in rapid fire succession. These neutron-heavy nuclei then undergo radioactive decay into stable elements. In this way, elements like iodine, gold, platinum, uranium, roughly half of all elements heavier than iron, are created in the cauldron of a single supernova explosion. Meanwhile, in a Type Ia supernova, a different kind of nucleosynthesis occurs, the furious burning of carbon and oxygen into a range of intermediate mass elements, particularly a lot of nickel and iron. Type Ia supernovae are prolific producers of iron group elements. In fact, the iron that makes our blood red and the nickel and cobalt in steel are spread through galaxies largely by Type Ia supernovae. Without those explosions, iron, the heaviest element that normal stellar fusion can produce in quantity, would remain locked in stellar cores or white dwarfs. Supernovae act as cosmic salt shakers, scattering these elements into the galactic soup. Think of a supernova as a cosmic seed, spreader. The heavy elements created over the star's life, and in its explosive death, are hurled into space at thousands of kilometers per second. In the aftermath, what was once the star's core might be a neutron star or black hole, but all its outer material, now enriched with a bouquet of heavy elements, mixes into the wider interstellar medium. Over millions of years, that gas will drift, cool, and mingle with other gas clouds. When new stars eventually form from those clouds, they inherit that enrichment. Planets condense from the leftover dust and gas around those new stars, and in some of those planets, life might one day arise, incorporating the atoms that were forged in a star long ago. To put it poetically, supernovae are the universe's way of taking matter cooked in one star's kitchen and delivering it as raw material for new worlds. In the early universe, before any stars had lived and died, there were only the lightest elements, hydrogen, helium, and trace amounts of lithium. The very first generations of stars were born from this pristine gas. Many of those first stars likely died in powerful supernovae that enriched their surroundings with the first heavy elements. Each subsequent generation of stars thus had more metals available. Our Sun was born from a cloud already seeded by countless prior supernovae. That's why Earth has an iron core and rich chemistry, and why life here can have elements like carbon, nitrogen, phosphorus, and so on. All those elements were gifts from stars that died before the Sun was born. Carl Sagan famously said, "We are made of star stuff." And this is not just metaphor, but scientific truth. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in the apple pie we might eat. These atoms were forged in stellar interiors and in the titanic explosions of supernova. We carry within us the ashes of long dead stars. Every time you hold a piece of gold jewelry or take a breath of air, you are touching remnants of a supernova's fury. In a very real sense, supernovae are our ancestors. They sculpted the elemental abundances of our galaxy. They made possible the chemistry that begot life. Realizing this connection can change the way we see a starry night. The sky is no longer just a beautiful backdrop. It's our ancestral home. We have stardust in our veins. Supernovae ensure that the universe is chemically rich and ever changing, rather than static and composed of only the simplest elements. A universe without supernovae would be a dull place. No rocky planets, no breath of air, likely no life. Having explored how supernovae forge the ingredients of planets and people, let us now examine what becomes of the stars themselves after the blast. What of the core that collapsed? That neutron, rich ball that was left behind? It may become one of the strangest objects in the universe. Let's meet the exotic corpses of massive stars, the neutron stars and black holes that emerge from the wreckage of supernovae. The corpses of stars, neutron stars, and black holes. After the immense explosion of a supernova fades, after the debris is cast into space, something often remains at the center. An ultra-dense stellar corpse, the condensed memory of the star that was. In the case of a core collapsed supernova, the core's collapse is halted by forces of quantum physics, leaving behind either a neutron star or, if the star was hefty enough, a black hole. These remnants are as fascinating as the explosions themselves, for they are among the strangest objects in the universe. Neutron stars, the spinning cinders. Imagine compressing the Sun, 333,000 Earth masses, into a sphere about 20 kilometers across, roughly the size of a city. The crush of gravity is so extreme that atoms cannot survive. Electrons have been rammed into protons to form neutrons, and matter as we know it is essentially transformed into a giant atomic nucleus. This is a neutron star. A sugar cube-sized amount of neutron star material would outweigh a mountain. The gravity at its surface is so strong that if you dropped a marshmallow from 1 meter above a neutron star, by the time it hit the surface, it would strike with the energy of an atomic bomb. These mind-bending facts belie the humble name, neutron star, but they are the reality of what a massive star's core becomes after a successful supernova explosion. Neutron stars often reveal themselves as pulsars, objects that emit beams of electromagnetic radiation that sweep around as the star rotates, like beams from a lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell. At first it was so regular that it was jokingly nicknamed LGM-1, hinting at the intrigue it caused. We now know pulsars are rapidly spinning neutron stars with intense magnetic fields, whipping around perhaps dozens or hundreds of times per second. The Crab Nebula's heart, for instance, is the Crab pulsar, spinning about 30 times a second, a lighthouse flashing in the wreckage of the 1054 supernova. Every pulse we receive is a rotation of that tiny neutron star, which carries on the legacy of the once mighty star by flashing its cosmic heartbeat centuries after the star's explosive death. Some neutron stars are even more extreme, magnetars, with magnetic fields 1,000 times stronger than a typical pulsar, capable of emitting flares that can disrupt Earth's ionosphere from tens of thousands of light years away. These bizarre objects are variations on the theme of neutron stars, matter in its most compact, stable form, holding perhaps up to 2 or 3 solar masses in that ultra-dense sphere. They gradually cool and slow down over time, but for many millions of years, they can spin rapidly and power energetic emissions, effectively signaling their presence to the cosmos. In a very real way, a neutron star is the remaining core of a star, still there after the supernova, not shining by fusion, but often emitting energy as it slows down, the stellar core's ghost, left haunting the site of the explosion. Black holes, the silent tombs. If the collapsed core of a star exceeds a certain mass, not even the pressure of neutrons can halt the collapse. In that case, gravity wins absolutely, and the core continues to shrink beyond the neutron star stage. It effectively vanishes from view, leaving behind a gravitational well so deep that not even light can climb out. A black hole is born. What remains is an object perhaps only a few kilometers wide, but containing more mass than our Sun. An object with no surface, only a point of no return, called an event horizon. Inside that boundary, space, time is curved into a pit from which nothing that falls in can escape. The core of the star has become a literal hole in the fabric of reality. Black holes were once theoretical curiosities, sprung from Einstein's general relativity equations, and considered by some to be too absurd to be real. Today, we have overwhelming evidence of their existence. Many stellar black holes announce themselves indirectly, often by interacting with a companion star. Gas from the companion may spiral into the black hole, heating up and emitting powerful X-rays before it vanishes across the event horizon. Cygnus X1, an X-ray source discovered in the 1960s, was the first strong black hole candidate. It likely formed from a massive star's collapse. Now we know many such X-ray binaries harbor black holes. Additionally, the ripples of gravitational waves detected in the past few years by observatories like LIGO and Virgo have come from mergers of stellar mass black holes, offering yet another confirmation that these dark remnants are out there. To stand on the surface of a neutron star or near a black hole's horizon is to confront the ultimate victory of gravity. Time itself behaves oddly in these realms. A clock on a neutron star's surface would tick significantly slower relative to one far away due to gravitational time dilation. Near a black hole, that effect becomes even more extreme. Time essentially stops at the horizon from an outside perspective. These effects, though counterintuitive, have been measured in weaker gravity regimes and match our theoretical predictions. In simpler terms, a neutron star, or black hole, is the outcome of a star's final battle with gravity. The star's core, unable to hold itself up, imploded and then found a new equilibrium as one of these exotic objects. They are the cinders or tombstones left after the brilliant supernova fire has gone out. Yet they are far from inert lumps. Neutron stars can light up their surroundings with beams of radiation or intense magnetic fields, and black holes, when fed by infalling gas, can become the engines for powerful X-ray sources or micro-quasars. Even in death, these stellar remnants can profoundly affect their environment. When we gaze into the night with radio telescopes or X-ray eyes, we occasionally hear the ticking of pulsars or see the flickering high energy glow of accreting black holes. Each is a supernova afterstory, the quiet, persistent end, note to a star's life. In the grand narrative, a massive star lives, explodes, and then either as a neutron star or black hole remains as a kind of monument. It's humbling to realize that the universe is littered with these tiny, dark remnants, hidden endpoints of countless stellar lives. We have now followed the star from cradle to grave, born in a cloud, shining steadily, dying in an explosion, and leaving behind a strange new object. Let us cast our eyes outward again to the expanding remnants of those explosions and see what becomes of the scattered star stuff itself. Supernovae do not merely vanish, they leave behind remnants that continue to glow and evolve, creating some of the most beautiful and intriguing sights in the cosmos. Ghostly echoes, supernova remnants. Long after the blinding flash of a supernova has faded from the sky, an ethereal apparition remains, the supernova remnant. These are vast, expanding clouds of debris, the scattered ashes of a star, still glowing from the energy of the explosion and the radioactive elements within. Supernova remnants are like cosmic smoke rings, beautiful, complex, and evolving over time, marking the spot where a star met its end. If we could watch a supernova remnant in fast forward, we'd see an almost spherical shockwave racing outward, plowing into the surrounding interstellar gas. Behind the shock front trails the tattered debris of the star, a mix of elements and newly formed radioactive isotopes, forming intricate structures as it interacts with itself and the environment. Immediately after the supernova, this cloud is extremely hot and shines brightly in X-rays. Over centuries and millennia, it expands and cools, beginning to radiate at optical wavelengths as well, and later in radio waves. Filamentary shapes appear, tangled ropes and sheets of gas shaped by magnetic fields and variations in density. One of the most famous remnants, the Crab Nebula, is a sight to behold even in a small telescope, a faint oval patch of light with subtle filament patterns. Long exposure photographs and modern space telescopes reveal those filaments in exquisite detail. Tendrils of glowing red, orange, where cooler gases like hydrogen and nitrogen emit visible light, interlaced with a bluish haze of electrons spiraling in the pulsar's magnetic field. The Crab Nebula is effectively powered from within by its pulsar. The neutron star's rotational energy keeps pumping out particles and fields that energize the nebula, making it shine far longer than it would from the explosion's initial heat alone. It's as if the remnant is a living organism with a beating heart that refuses to let the glow die out. Another remarkable remnant is Cassiopeia A. Although its originating supernova, around 1680, was not widely observed, Cass A is a young remnant about 350 years old, and high-resolution images show an asymmetric, lumpy shell of gas about 10 light-years across. It's rushing outward at thousands of kilometers per second. By studying Cass A, scientists have gleaned insights into how the supernova explosion might have been irregular, not a perfectly symmetric blast, but one that ejected knots of material in some directions more than others. Cass A's debris is rich with elements like oxygen, sulfur, and silicon, clearly marking it as the remains of a massive star. In the center lies a faint neutron star, cooling in quiet isolation. The ghost of the star is not at rest. It's expanding and colliding with its surroundings, sending out shockwaves that heat the interstellar medium and even accelerate cosmic rays that zip through our galaxy and occasionally reach Earth. Supernova remnants can be breathtakingly beautiful. The Veil Nebula in Cygnus, for example, is the remnant of a supernova roughly 8,000 years ago. It now spans about 3 degrees of the sky as a wispy lacework of ionized gas. Through a telescope, parts of it appear as delicate filaments, so thin and gossamer that one can scarcely imagine the violent event that created them. These filaments are shock fronts seen edge on, where the shell of the remnant is plowing into interstellar space and causing the gas to glow. What was once a catastrophic blast has, over millennia, become a faint, ghostly veil decorating the sky. Beyond their beauty, supernova remnants are profoundly important to the ecosystem of the galaxy. As the remnant expands, It sweeps up and stirs the interstellar medium, mixing the new heavy elements from the explosion into the cosmic clouds. This enriched material will one day become part of new stars and planets. The shock waves can trigger the collapse of nearby gas clouds, perhaps inducing new stars to form, so one star's death can sow the seeds for the birth of others. At the same time, remnants inject energy into the galaxy's gas, heating it and driving turbulent motions that can inhibit immediate star formation elsewhere. This feedback helps regulate how galaxies evolve, preventing them from turning all their gas into stars at once. Over tens of thousands of years, a supernova remnant will gradually dissipate. Its shock slows to the speed of sound in the surrounding medium and eventually merges with the general interstellar environment. By then, the heavy elements are well blended into the galactic reservoir. Only faint traces might remain, perhaps slightly higher concentrations of certain elements in that region of space, or cosmic ray particles that were accelerated by the remnant's shock still wandering the galaxy. Thus, a supernova remnant is the intermediate chapter of the story between the violent death and the eventual recycling of the star's substance into new cosmic structures. It's the long, fading echo of the supernova's shout. By reading the glowing wisps and shock fronts, scientists can decode details of the explosion, how fast the material is moving, what it's made of, and how it's interacting with its surroundings. Even long after a star has died, its remnant continues to tell its story. In every supernova remnant, we see a snapshot of change in action. They are elegant reminders that even after catastrophic destruction, there is quiet creation and transformation. The scattered atoms will someday cool and perhaps gather again in dark nebulae, ready to form the next generation of stars. In that way, a ghostly remnant is not an end, but a bridge to new beginnings. Stepping back from individual remnants, we consider the grand scale once more. Supernovae, whether near or far, serve as brilliant beacons in the cosmos. Their light and energy travel across vast distances, sometimes allowing us to measure and understand the universe itself. In the next section, we'll explore how these stellar catastrophes become cosmic lighthouses and what they have revealed about the space between the galaxies and the fate of the universe at large. Cosmic beacons, light across the universe. Supernovae are not only agents of cosmic recycling, they also serve as signposts on the grandest scales. When a star explodes, it becomes, for a few weeks, one of the most luminous objects in the universe. A single supernova can outshine an entire galaxy of billions of stars. This extraordinary brilliance means that supernovae can be seen across immense distances, allowing astronomers to use them as cosmic beacons or lighthouses. By observing supernovae in remote galaxies, we can measure those galaxies' distances and probe the expansion of the universe itself. Among all supernovae, the type Ia have proven especially valuable in this regard. Because a type Ia results from a white dwarf reaching a critical mass and undergoing a thermonuclear explosion, the amount of energy released is fairly uniform from one event to another. In more practical terms, most type Ia supernovae reach about the same peak absolute luminosity, like bulbs of nearly the same wattage. If we observe a type Ia in a distant galaxy and measure how bright it appears, we can compare that to the known true brightness and deduce its distance. A classic use of the inverse, square law of light. This is why type Ia supernovae are termed standard candles. In the late 20th century, astronomers began using these standard candles to chart the universe. They painstakingly observed type Ia supernovae in far-away galaxies, billions of light years distant. By doing so, they aimed to measure how fast the universe was expanding at different times in the past. The expectation was that the expansion should be slowing over time as gravity tugged on galaxies. But the supernova beacons told a different story. In 1998, two independent teams analyzing distant Type Ia supernovae made a shocking discovery. Those supernovae were dimmer than expected in a decelerating universe. The simplest explanation was that the expansion of the universe has been speeding up, an acceleration driven by some mysterious force or energy inherent to space itself, later dubbed dark energy. It was a revelation that earned the 2011 Nobel Prize in Physics for the team leaders. Think about that. By observing the dying flashes of stars in galaxies halfway across the observable universe, we gleaned insight into the fundamental behavior of the cosmos on the largest scale. Each supernova that appeared in those distant galaxies, tiny dots of light on telescope images, carried within it the information needed to trace the history of cosmic expansion. The lives and deaths of stars, recorded as brief flickers in the night, became evidence for a new ingredient of the universe that now appears to dominate its fate. Supernovae also help us measure distances closer to home and map the three-dimensional structure of the universe. Even before the discovery of cosmic acceleration, astronomers used Type Ia supernovae to refine the Hubble constant. By comparing distances from supernovae with the redshifts of their host galaxies, they calibrated the relationship between redshift and distance. This led to a better handle on the size and age of the universe. To this day, monitoring supernovae in distant galaxies remains crucial for improving our understanding of the universe's expansion history and for probing the nature of dark energy. Apart from cosmology, supernovae act as beacons that illuminate their local environment. As their light travels through space, it can be absorbed or re-emitted by any intervening gas or dust. By studying the spectrum of a supernova, we can detect absorption lines from elements in the host galaxy or in between galaxies. In one famous case, light from a distant supernova passed through the vicinity of a foreground galaxy cluster and was gravitationally lensed, producing multiple images of the supernova that reached Earth at different times. Astronomers observed one image of that supernova and, by understanding the lensing delay, successfully predicted when the second image would appear a couple of years later, and they saw it right on schedule. This kind of phenomenon turns supernovae into probes of the distribution of matter in the lensing clusters. Even without such exotic effects, every supernova in a distant galaxy provides clues about that galaxy, its composition, its star formation, history. When a massive star explodes in, say, a galaxy tens of millions of light years away, we detect it and thus learn that this galaxy is actively forming stars. Supernova surveys have catalogued thousands of supernovae in all types of galaxies, revealing patterns. For instance, Type II and Type IB/C supernovae occur only in galaxies with ongoing star formation. You won't find a massive star supernova in a quiescent elliptical galaxy, because such galaxies no longer have massive young stars. On the other hand, Type Ia supernovae occur in both star-forming galaxies and old elliptical galaxies, since every galaxy has some population of binary white dwarfs or old stars that can produce them. The sheer number of supernovae now catalogued has allowed us to identify rare subclasses and see subtle differences. We found peculiar types often by catching them in other galaxies. No two supernovae are exactly alike. Each explosion has its quirks, but they cluster into families that we can study statistically. And all of this has been possible because the universe provides an endless supply of distant supernovae, and we've developed the technology to monitor the sky systematically. Technology is rapidly advancing this field. The Vera C. Rubin Observatory in Chile, with its legacy survey of space and time, is expected to discover on the order of 10,000 supernovae per year in the coming decade. It will effectively make a high-definition movie of the optical sky, catching transient events like supernovae on a nightly basis. We will have supernova light curves and spectra in amounts previously unimaginable, likely uncovering new oddball explosions and further refining the use of supernova as cosmic yardsticks. There's also something profoundly moving about seeing supernovae in distant galaxies. It drives home the point that the life and death of stars is a universal saga. When you see a tiny, bright dot on an image of a galaxy tens of millions of light years away, knowing it's the death throe of a star, possibly someone else's sun in that galaxy, you feel an intimate connection with a distant part of the universe. These events link us with other galaxies, not just in a physical sense, but in a narrative sense. The story of stars and supernovae is a thread that runs through the cosmos, binding our Milky Way to the remotest spiral. From the closest supernova observed with the naked eye in centuries to the farthest detected by our most sensitive telescopes, each is a flash of enlightenment across space and time. Through them, the universe has communicated its nature to us. They have been beacons not only of light, but of knowledge, guiding us to understand cosmic distances, the expansion of space, and the history of galaxies. We have now covered supernovae from the tiny scale of atomic nuclei in a collapsing core to the vast scale of the accelerating universe. It seems fitting, as we near the end of our journey, to reflect on what it all means, how the death of stars is connected to the existence of life, and what philosophical insights we can glean from the cycle of stellar death and rebirth.
Danger in the sky, the threat of supernovas.
Supernovae captivate us with their brilliance and enrich us with their stardust, but they also remind us that the cosmos can be dangerous. A star's death is not only a spectacle, it unleashes a storm of radiation and high-energy particles that can have profound effects on its surroundings. If such an explosion happened close enough to Earth, the consequences could be severe for our planet's biosphere. Have supernovae ever affected life on Earth? Could they in the future? These questions take us from cosmic wonder to an edge of concern. Fortunately, the odds of a supernova occurring very near Earth in our lifetimes are low. Our Sun is not massive enough to explode, and among the nearest stars, none within the critical distance are likely to go supernova soon. The general consensus is that a supernova closer than about 25 to 50 light years could pose a serious threat, primarily by bathing Earth in intense high-energy radiation and a barrage of cosmic rays. The immediate effect of such radiation on Earth's atmosphere would be to erode the ozone layer that shields us from the sun's ultraviolet rays. With the ozone layer damaged, harmful solar UV would flood the surface, potentially causing mass die-offs, especially in marine ecosystems where plankton, the base of the food chain, are vulnerable to UV. Scientists have searched for fingerprints of past supernova effects on Earth. One intriguing find lies in ancient seabed deposits. An excess of the radioactive isotope iron in sediment layers dated around 2,003 million years old. Iron 60 is produced in supernovae and has a half-life of 2.6 million years, so finding it on Earth's surface implies a relatively recent nearby supernova. Indeed, some studies suggest that one or more supernovae occurred about 2.5 million years ago at 150 light-years away, possibly affecting Earth's climate or contributing to minor extinctions. Another study links increased radiation levels to a minor extinction at the end of the Pliocene epoch, speculating a supernova as a cause. While these connections remain under investigation, they highlight that Earth is not completely immune to astrophysical events. If a supernova happened, say, within 30 light-years, the radiation pulse could cause a mass extinction by wrecking the ozone layer and bombarding life with UV. The geological record does show some unexplained extinction events that some scientists have playfully speculated might be due to nearby gamma, ray bursts, or supernova. Which nearby stars could pose such a threat? The good news is, none of the very closest stars are of the type to explode soon. The nearest massive stars are dozens to hundreds of light-years away. Betelgeuse, the red supergiant in Orion, often comes up in discussion. It's about 650 light-years away. When Betelgeuse does explode, it will likely put on a spectacular show, potentially bright enough to see in daytime, but it's too distant to harm Earth aside from perhaps some subtle effects on our upper atmosphere. Candidates often mentioned include stars like Antares, or more significantly, a star system called IK Pegasi, which includes a white dwarf that could become a Type Ia supernova in the far future. However, by the time IK Peg's white dwarf accretes enough mass from its companion to explode, it will likely have drifted farther from us. Another potential danger comes from gamma ray bursts, extremely energetic jets that can accompany certain supernova-like events, especially the collapse of an especially massive, rapidly rotating star into a black hole. If a gamma ray burst were pointed directly at Earth from a few thousand light years away, the focused beam of gamma radiation could be devastating. Even from much further than the supernova's general radiation would be dangerous. Fortunately, such GRBs are rare, and the Milky Way is big. No known GRB progenitor is close enough and aimed at us to cause concern at present. One speculative idea is that a GRB might have caused the Ordovician mass extinction 450 million years ago, but this remains unproven and perhaps unprovable. So, while the risk is never zero, it appears that at this moment in cosmic time, Earth is not in the crosshairs of any nearby supernova candidates. We can be grateful for the margins the cosmos has given us. We live bathed in the gentle radiation of a stable, middle-aged star, far from the volatile furnaces that would endanger us. Even so, the concept of supernova threats has spurred some interesting science. For instance, astronomers have surveyed the sky for traces of past supernovae and keep tabs on the massive stars within a few hundred light years. We are effectively monitoring the environment of our solar neighborhood for potential supernova weather. It's sobering to think that events light years away can influence life on a planet, but it's also part of the dynamic nature of the universe. Human civilization might someday have detectors that could provide an early warning if a nearby star's core collapses. We already have neutrino detectors that would give us a few hours' notice of a supernova. Neutrinos escape the collapsing core before the light from the explosion gets out. Thankfully, the notice will likely be for an exciting show, not a doomsday event. Supernovae, then, are a double-edged sword, creators and destroyers. They likely helped enable life by forging elements and shaping environments, but in rare cases, they might also snuff life out. The very cosmic events that made our existence possible could, under different circumstances, pose a lethal threat. For us, the bottom line is that we should continue to watch the stars, both out of scientific curiosity and for prudent awareness. The night sky is mostly peaceful, but it has its violent moments. Knowing that our planet has likely survived nearby supernovae in the past, we carry on under the stars with both awe and respect. Now that we have contemplated the dangers supernovae might pose, let's turn our attention to some of the most extreme kinds of stellar explosions known, those that push the very limits of power, and those curious cases where a star's death might not produce much visible light at all. Extraordinary explosions, superluminous and pair, instability, supernovas. Just when we might think we've seen it all, the universe surprises us with stellar explosions, even more powerful or peculiar than the standard supernovae we've discussed. In recent decades, astronomers have identified a class of supernova so luminous that they outshine normal supernovae by 10 or even 100 times. These are the superluminous supernovae, cosmic blasts so bright we can detect some from the early universe, billions of light years away. On the other end of the spectrum of weirdness are pair instability supernovae, theorized explosions of the most massive stars that completely obliterate the star. Both types push the boundaries of how stars live and die. Superluminous supernovae. Imagine a star explosion so bright that for a time it can outshine an entire galaxy. In 2007, astronomers observed a supernova, SN 2006 July, in a relatively nearby galaxy that was over 100 times more luminous than a typical Type II supernova. It stayed bright for many months, This was one of the first confirmed superluminous supernovae, and it left astronomers both excited and puzzled. What could cause such an extraordinary outburst? Since then, many more SLSNE have been found, often in small, distant galaxies with very active star formation. These events reach absolute magnitudes of 21 or 22, meaning at peak, they can be 10 to 50 billion times the brightness of the Sun. What powers such brilliance? In some cases, it may be a central engine, perhaps a newborn magnetar left by the explosion, which pumps energy into the ejector as it spins down. As the magnetar's immense rotational energy is transferred to the expanding gas, it keeps the gas hot and glowing much longer and brighter than usual. In other cases, the cause might be the collision of the supernova's ejector with a dense shell of gas around the star, a shell the star shed in a dramatic eruption before it exploded. The kinetic energy of the explosion gets converted into light in this collision, a bit like a cosmic traffic accident, producing a brilliant flare. SN 2006 GY, for example, is thought to have been such a case. A very massive star might have thrown off a large amount of mass in an eruption or series of eruptions, and then shortly after, its core collapsed and it exploded. The supernova blast wave slammed into the previously expelled gas, producing an extremely bright, long-lasting flash. These types of interactions are classified as type 2 supernovae, and indeed, some events observed historically as supernova imposters, where a star suddenly brightened but didn't die, were likely these precursor eruptions. The prime example is Eta Carinae, which in the 1840s became one of the brightest stars in the sky for a few years without exploding. It ejected a massive bipolar nebula and survived. Eta Carinae remains with us, albeit much dimmer now, and is still a ticking time bomb for a future supernova. Its great eruption was a supernova imposter, a false alarm, one might say, hinting at the chaos within the star. Many superluminous supernovae seem to involve stars that had similarly big eruptions shortly before final collapse, essentially setting themselves up for an especially luminous demise. Pair instability supernovae, when stars obliterate themselves. Now consider the upper limit of stellar mass, say a star with 150 to 250 times the mass of our Sun, something only likely to form in pristine conditions. In such a monster star, during its late evolutionary stages, a strange thing can happen. The core becomes so hot that the energy of gamma ray photons being produced starts spontaneously converting into matter and antimatter pairs. This process robs pressure from the core. The sudden drop in pressure causes the core to contract dramatically, the pair instability. This contraction raises temperatures even further, igniting runaway fusion. If conditions are just right, this results in an explosive thermonuclear burning that unbinds the star completely. A pair instability supernova. The star is blown to smithereens. No black hole is formed, because even the core is blasted apart in the explosion. Pair instability supernovae are purely theoretical for now, though there are candidate events. They would be extremely luminous and long-lasting because the star is being burned and ejected entirely. SN 2007 BI is an example that was proposed as a pair instability supernova. It occurred in a small, distant galaxy and was exceptionally bright and slow to fade, with indications that tens of solar masses of nickel were synthesized. If indeed it was such an explosion, it means somewhere out there, a star of around 200 solar masses lived fast and died in a unique way, completely annihilating itself. There are also pulsational pair instability scenarios, where a massive star doesn't quite blow itself up in one go. Instead, the pair production instability causes a partial collapse and eruption that throws off the star's outer layers but leaves the core intact. The star survives that pulse for a while, until it later perhaps pulses again, or eventually the core collapses to a black hole once enough mass is lost.
These pulses can also produce bright transient events. The recently observed oddball IPTF-14HLs, a star that appeared to undergo multiple explosions over a few years, might be an example of a pulsational pair instability event. It baffled astronomers by acting like a supernova that just wouldn't finish dying, brightening, fading, then brightening again 5 separate times over more than 2 years. One hypothesis is that it was a star, perhaps 100 solar masses, that had a series of internal pulsations, blowing off shells of material in eruptions, but not yet destroying its core. Eventually, perhaps that star will finally undergo core collapse and explode for good. But in the meantime, we witnessed a zombie supernova. This shows how even in death, some stars can take an unusual path. Hypernovae and gamma ray bursts. While on the topic of extremes, it's worth mentioning the term hypernova, often used to describe an exceptionally energetic supernova, typically one associated with a long-duration gamma ray burst. In the 1990s, as gamma ray bursts were being localized to distant galaxies, it became clear that at least some long GRBs were linked to the deaths of very massive stars. Essentially, if a very massive star collapses and forms a black hole, and if it has enough angular momentum and magnetic fields to produce collimated jets, we get a GRB, a blast of gamma, rays shooting out along the rotation axis of the star. If Earth lies along the path of one of those jets, we see a GRB. Meanwhile, the star's remaining material still explodes in what we would call a supernova, specifically a type IC, since the star has likely shed its hydrogen and helium envelopes. These explosions can be extremely energetic, because the jets deposit additional energy into the ejector. SN 1998BW, coincident with GRB 980425, was the first strong case of a GRB-related hypernova. It was unusually luminous in radio and had very high expansion velocities. Since then, a few dozen GRB supernovae have been observed, confirming that at least some of the brightest explosions come from this engine-driven mechanism. All these extraordinary explosions, superluminous supernovae, pair instability events, pulsational multi-explosion stars, and hypernovae with gamma ray bursts, demonstrate the incredible range of fates that befall the most massive of stars. They are relatively rare, but they are crucial to testing the limits of physics. They show us what happens in stars at the upper mass limits, how the first stars might have died, and how the most extreme energies in the stellar regime are released. These explosions also stretch our vocabulary and our understanding. They have forced astronomers to expand theories, to include magnetar-spin, down energy in light curves, to consider matter, antimatter pair creation in stellar cores, to account for asymmetric jets ripping a star apart. They are the flamboyant outliers of the supernova family, but often in those outliers lie insights into regimes of nature we cannot replicate on Earth. On the flip side, just as some stars explode more spectacularly than expected, some massive stars may fail to explode at all, collapsing into darkness with hardly a trace. Not every stellar death results in a bright supernova. Next, we will explore these enigmatic failed supernovae, cases where a star's core collapses into a black hole and yet produces little or no visible explosion. The ones that failed, when stars collapse without a bang. Throughout our journey, we have assumed that when a massive star's core collapses, a titanic explosion, a supernova, inevitably follows. But nature has a more silent ending on the menu as well. Sometimes a star can die with hardly a whimper. In these cases, the core implodes, and instead of blasting the star's outer layers apart, it simply pulls them inward, swallowing the star into a newly formed black hole. These are the so-called failed supernovae. For a long time, failed supernovae were speculative. Simulations of core collapse hinted that if the conditions weren't just right, say, if the shockwave lost too much energy and couldn't be revived by neutrinos, the infalling star might never explode. The core would become a black hole, and aside from perhaps a brief cough of energy, the star would just disappear. What would that look like to an observer? Perhaps a star would brighten a little as the core started to collapse, then fade away forever. In recent years, astronomers have actually been looking for this phenomenon. How do you catch a star failing to explode? One approach is to watch many supergiant stars in nearby galaxies over time and see if any simply vanish. Remarkably, one candidate has emerged. A star in galaxy NGC 6946 was observed to brighten modestly in 2009, and then by 2015, it had vanished from optical view. It was a hefty red supergiant before it disappeared. This object, nicknamed N6946 BH1, likely underwent core collapse and formed a black hole without a successful supernova. There was a small burp of light, a sort of mini explosion or outburst, when it brightened in 2009, but no big supernova explosion followed. The star just became a memory, detectable now only as a faint infrared source. It appears we observed a failed supernova in real time, the first of its kind. One hypothesis is that the core of the star collapsed directly into a black hole, and the weak shock generated wasn't enough to eject the star's outer layers. Instead, most of the star fell into the black hole. The small amount of energy released by the core collapse created a faint transient event. Indeed, some very massive stars might shed a bit of their envelope or produce a low-energy explosion, but still end up mostly collapsing, what we call a fallback supernova or failed supernova. Why would a star fail to explode? It likely depends on mass and the detailed physics of the core collapse. It's thought that stars above roughly 17,020 solar masses might have a harder time exploding. If the core forms a black hole quickly, it can swallow infalling material so fast that the shock is smothered. Alternatively, if the star has a very large, extended envelope, the shock might stall out in that envelope without unbinding it. The evidence is mounting. We see fewer supernovae from the very most massive red supergiants than expected, perhaps because those stars quietly collapse instead. It seems quite plausible that many black holes in our galaxy formed without a bang. What would a failed supernova look like up close? Suppose we were watching a massive star in its final days. We might see it start to dim and brighten irregularly as it undergoes convulsive nuclear burning of silicon. Then, perhaps, a sudden but short-lived glow. The outer layers briefly heating as the core collapses, and maybe a weak shock travels outward. The star might expel a small fraction of its material. Neutrinos would flood out, possibly the only strong cry of the dying star. Then, the light fades. The star's surface material, which didn't get enough of a push to escape, rains back down into the black hole. To an optical telescope, the star simply vanishes. In NGC 6946, astronomers literally have before and after images. The star was there, and then it wasn't. If such a failed supernova happened in our galactic neighborhood, we might detect it not by light, but by an outpouring of neutrinos, ghostly particles released by the imploding core without a bright optical display. Future neutrino observatories could potentially catch these subtle signals of a star collapsing directly into a black hole, giving us a heads up even when the star itself disappears in darkness. Failed supernovae are a chilling reminder that not all stars go out with a glorious finale. Some simply cease to shine, leaving no glowing remnants, just an invisible gravitating mass. If massive stars can collapse quietly, there might be many dark corpses drifting in galaxies, undetected unless they interact with a companion or surrounding gas. An entire population of silent black holes could be lurking, each marking a life that ended without fanfare. Even so, such a death would not be entirely without a signal. A collapsing star still floods its core with neutrinos and rattles space-time with gravitational vibrations, even if no light escapes. Future neutrino observatories and gravitational wave detectors might pick up these subtle clues of a failed supernova, alerting us to a cosmic death that optical telescopes would miss entirely. The search for failed supernovae continues. With more years of data and more eyes on the sky, we hope to better quantify how often stars vanish without an explosion. It's an important piece of the puzzle of stellar evolution. It affects how many supernovae we count versus how many black holes we expect, and it tells us about the upper limits of how a star can die. We have journeyed now through nearly every twist and turn in the saga of stellar death, from spectacular hypernovae to silent collapses. All that remains is to step back and reflect on the grand picture one more time. Why do supernovae matter on the deepest level? What do they mean for us, living on a small planet around an ordinary star? In our final section, we consider the philosophical reflections that supernovae inspire. How, in their death, stars sow the seeds of new life, and how we, in turn, owe our existence to these cosmic catastrophes.
Epilogue. From death comes life.
We have traveled among giant stars and witnessed their demise. We have walked through cosmic time to see how each supernova, in destroying a star, contributes to the creation of something new. Now, at the end of our journey, we pause and look back at the grand tapestry we've been part of. A profound pattern emerges. In this universe, death is not simply an end, but a transformation. The death of stars is intimately linked to the birth of everything we hold dear. Consider the atoms that compose our bodies. Every breath we take, every glance we cast at the stars, we do so with atoms that were once inside of stars. Many inside stars that blew themselves apart long before the Earth existed. It took the violent sacrifice of countless stars to sprinkle the cosmos with carbon, oxygen, iron, and the rest of the periodic table. Only then could the clouds that formed our sun and Earth have the ingredients to build rocky planets and living organisms. In a very literal sense, we are the children of supernovae. Each one of us is a composite of stardust, forged in stellar hearts and scattered in stellar graves. This truth carries deep poetry. The universe has a cycle akin to the seasons. Stars are born, live gloriously, and die. From their remains, new stars take form. Out of destruction comes creation. It is a cycle that has been ongoing for billions of years, gradually enriching the cosmos and increasing its complexity. When we look at the night sky, we see the gleam of stars that will one day cease to exist. Some will quietly fade, others will end in spectacular explosions. Yet from their ruin, new worlds may one day blossom. Perhaps somewhere in our galaxy, a supernova exploding today is seeding a nebula that, in 5 billion years, will give rise to a star and planets. And perhaps life and consciousness that will look up and wonder, as we do. There is a powerful philosophical echo here, impermanence and renewal. Stars, for all their immense power and longevity compared to our lives, are not eternal. They are born from dust and gas. They return to dust and gas. But in that returning, they fertilize space for new stars. The cosmos recycles itself. Endings are not only terminations, they are also beginnings in disguise. A supernova is an ending for a star, but the beginning of a nebula, the beginning of new chemical dispersal, the potential beginning of future life cycles. We humans, existing on our small planet, owe our existence to this grand and sometimes violent cycle. Perhaps counterintuitively, we owe our lives to explosions so distant in space and time we cannot name the sources. A star had to die for you to live. And not just one star, many. The gold in your jewelry, the iodine in your thyroid, the calcium in your teeth, these probably came from different supernovae scattered across the Milky Way over the past 10 billion years. You are an amalgam of stellar legacies. Realizing this connects us intimately to the cosmos. The boundary between us and the universe blurs. The universe is within us, literally. When ancient people saw supernovae, they often imbued them with divine or mystical significance. Today, through science, we see no less magic. If anything, the magic is amplified by understanding. Knowing that a point of light is a star ripping itself apart, and that such events made the world we know possible, adds layers of meaning to that transient star in the sky. In a way, we can view supernovae as the universe's way of keeping life possible. A universe without supernovae would be static and impoverished in elements, perhaps devoid of complex chemistry and life. Supernovae inject dynamism. They ensure that the universe doesn't stagnate, that material cycles through different forms. Out of the quiet, cold hydrogen of the early cosmos, supernova helped cook up the rich, warm complexity of planets and living organisms. As we conclude our cosmic journey, let's picture one more scene. We stand on a hill under a clear night sky. Above us, the Milky Way arches, a river of starlight. We know now that scattered among those stars are supernova remnants, the ghosts of long-dead suns, and perhaps a few stars that even now, as we watch, are living out their final moments, soon to explode. We feel the gentle night breeze, we hear the quiet of Earth, but we are aware of a colossal, ongoing drama playing out in silence overhead. One of those pinpoints of light might suddenly flare bright in our lifetimes, a nearby supernova gifting us a celestial spectacle, and while we gaze in awe, perhaps a being in another star system far away might at that same moment witness our sun as just another pinpoint in their sky, not knowing that around it a species capable of reflection and gratitude has arisen, thanks in part to
ancient supernova. The cycle of stellar life and death is far grander than us, yet we find our own story within it. It instills humility. We are small and our lives flicker more briefly than any star, but also great connection. We are a way for the cosmos to know itself, born of its very fires. When a supernova's light reaches our telescopes after traveling for centuries or millennia, it is almost as if the universe is telling us its story, whispering through the night. See, this is how I renew myself. This is how, from death, I create life. And so, the next time we look up at the stars, we can remember that we are part of this cosmic story. The iron in our blood was once in the core of a massive star that died in a blaze of glory. The oxygen we breathe was forged in the belly of stars and spread by supernova winds. We are the universe, made conscious. We are star, stuff contemplating the stars. Supernovae are chapters in the universe's story, dramatic, violent chapters that nonetheless lead to creativity and rebirth. We began with cosmic death and rebirth. We end recognizing that they are one and the same. In the grand cycle of the cosmos, destruction and creation are intertwined. The universe evolves through this cycle, and we are one expression of its continual rebirth. In understanding supernovas, we understand ourselves a little better. Ephemeral, yet inextricably connected to eternity, fragile yet born of explosions, finite yet integral to an infinite cosmic cycle. The stars have died to give us life, and in their memory, we live on and wonder, adding our own chapter to the saga of the cosmos.